Sorry guys, I'm very stupid. I forgot to click on on start. I forgot to start the stream. I just started it in my streaming software, but I didn't start it here on YouTube. So sorry, I was talking for five minutes. Stupid me. Sorry. Okay, so let's start from the top. Okay, so first, I hope you're all doing well, and I'm sorry that so many of you came up empty with my raffle. And like I said in the video, I mean, there were 508 entries and I had 2 modules to give away. So there was bound to be some disappointment. So sorry, but still, I was kind of happy with the idea that I had to announce the winners. And I hope that you got something out of that. I mean, at least you got a noise generator and some ADC madness. So I hope that could kind of make up for it a bit. Yeah, on another note, I also, when I watched the replay of the last stream, I kind of noticed that my voice was very low and I had to like really bump up the volume on my laptop to hear it properly. So I decided to slap a compressor on there and just boost the volume a bit. So let me know if this is loud enough, like if it's better. I can still bump it up a bit more, but also if it's clipping, please also tell me. So with that out of the way, what are we doing today? Well, I must confess that I kind of lured you here, not under false pretenses, but I mean, I called this light emitting filter, and we are going to see if we can modify my diode filter to work with LEDs. That's kind of the end goal. But I would like to save this for last. Also, I mean, because it's so bright outside that I'm fearing that you couldn't see the LEDs. But no, the actual reason is that before we get into the LED stuff, I would actually like to talk about some improvements that I've made to my filter design. Because, I mean, it's always this way. Like when I publish a video on a circuit that I've done, it's usually a version of the circuit that I'm confident in that it it works okay, like that people will get some use out of it. But of course, it's never perfect, and there's almost always stuff that I would like to improve upon. Like you see with my VCO, like I keep releasing videos, and I did a live stream recently on the triangle output to kind of improve it. So yeah, I mean that's kind of like the way it goes. So with the filter, the thing is that the circuit that I based my Eurorack module on, the circuit is functional, like it does work, like there's no fatal flaws, there's nothing that would completely disqualify it. But I was kind of unhappy with the way that I handled the CV processing. And I already was unhappy with it like when I did the video, but I did not have like the proper solution. Like I knew what I wanted to do, but for some reason, like whenever I was Googling it, like I couldn't find the solution that I was looking for. So in the end, I settled on what I had and decided to go with it. But like just a few days later, actually, I stumbled upon a solution that I saw, and at first I thought like, not sure if this is gonna work, but it works perfectly. So this is kind of what I would like to share first of all. And so I'm going to warn you, like the first leg of this stream is going to be mostly in the circuit simulator. And we're going to talk a bit about, just the CV processing, and I'm just going to show you like what I was unhappy with, and then the solution that I found. And of course, afterwards we're going to go to the breadboard, we're going to try it out, and then once all of this works, we are going to try it with diodes. And I hope, I'm not sure if I hope that I don't burn any, because I mean, seems to be very popular on YouTube to trash stuff and destroy stuff. So maybe it won't be so bad if we burn some LEDs, but we will see about that, I guess. So let's go into my circuit simulator. So I hope you can see. but like always, I'm just going to pretend that you can see, and I'm just going to go on. If it doesn't work, let me know. So what are we looking at here? Well, it's basically it's like exactly the circuit that I based my module on. So you can also find this under the Eurorack module video. In the description, you can find the FileStat link that will lead you to this exact circuit. And I guess most of you have watched the video. If you haven't, I'm not going to go through it like completely again because I feel like it would be a bit redundant. And instead, I'm just going to kind of go at the CV processing right away. If we take a look at this, I mean, most of you probably remember how this works, but still, I'm going to walk through it like from the beginning. So, I mean, the idea here is that we use the CV to kind of control these two op amps, like this op amp up here, this op amp down here, and by increasing the value of the CV, so by raising the voltage at the output of this op amp, we would make this op amp, increase its output voltage, and we would make this op amp decrease its output voltage. And so in the end, like in effect, the voltage here would rise and the voltage here would drop, like it would go negative actually. And I can show this to you in the simulation. Right now the output voltage here is very high, so we're at 1.6 volts. And so you can see that I'm not a liar by looking at this node up here, and down right in the corner you can see like a little it says voltage or V equals, and right now it's swinging between 1.2 volts and 1.1 volt approximately. And then if I go down here, we can see that it's basically swinging like it's the same value but just negative. And now if I turn the cutoff knob down, then we can see that the voltage up here drops. So we're now like about 400 millivolts below what we had before, and here the voltage actually went up. So we come from minus 1.2 volts, and now we're at minus 800 millivolts. So also 400 millivolts difference there. And that was basically just the way that we control the resistance value of these diodes. So the bigger the voltage difference between the top here and the bottom down here is, the wider open the LEDs get basically, and the more their resistance drops, you could say. And from there, it's basically like any basic resistor capacitor filter. So if the resistance on this path drops, then these capacitors get filled up quicker, and then they basically filter the wave less, you could say. So here if I turn the cutoff knob completely the other way, then the voltage here increases again. Now it's very high here and it's very low here. And so the caps get filled very quickly, and we have like down here you can see the output, and you can see it's like it's nearly perfectly square. So, and it's all controlled by this op amp over here. And there was one thing that was rather a big problem. That kind of, I mean, this is kind of the thing that kind of threw me off track, because I really didn't know how to deal with this. So the problem is that if we increase the output voltage of this op amp, then the cutoff frequency basically rises. So the square wave down here gets more square. So you can see this, if I pull this down completely, then the square wave gets rounded at the output. And if I pull it completely in the other direction, it gets more angular. But the problem is that there is a point beyond which this doesn't work anymore. So if the voltage at the output of this op amp gets too high, then our filter starts like doing really weird shit. And I surmise that the problem is that if the voltage difference between this point up here and this point down here gets too big, then these diodes, like the resistance value of these diodes, like really drops. I mean, the relationship is basically exponential. So a linear increase in voltage between these 2 points sees an exponential increase in current, through these diodes. And so at the top end, this is just my suspicion, at the top end, like the current through here increases so much that we then get these weird effects. I can't exactly explain to you why we get those effects, but that seems to be the problem. And so what I had to do was I needed to find a way to make sure that the voltage here at the output of this op-amp doesn't rise beyond a certain threshold. And the way that I decided to do this is basically, I mean, this is kind of the flashier version, but it was basically just with these 3 diodes. Because the idea is, and I'm sure you've seen this in other circuits, this is a kind of like a widespread idea that you see often, that you use these diodes to ground to clip a signal. Like normally you would see a string of diodes going to ground, and then normally you would see another string of diodes coming from ground and going to the point where the signal is, basically. And that way you can clip a signal at the top and at the bottom, because the way that this worked was as long as the voltage at this point is relatively low. So let me pull all of these down. Oh, there's still one. Yeah, here. Oh no, cutoff is negative. Oh yeah, that's. I wanted to fix this. So in the fast stat simulation of the of this filter, I still have the cutoff knob connected to -12, even though in the video I said it should be connected to ground. So let's connect it to ground. Okay. So I will pull this here, and right now we have 10 millivolts here. And as we know, or as I just explained, the amount of current that is flowing through a diode or a string of diodes, so going from up here down to ground, is determined by the voltage difference between this point up here and this point down here. And right now we have 10 millivolts here, we have 0 volts here because it's ground, and so the diodes they're basically blocking. They're not completely blocking, then it's not like an open circuit, but they don't, there's no current flowing really between through them. But if we do increase, like if we turn the cutoff knob, then we can see that the voltage here is rising. We're now at 700 millivolts. We're still at 0 volts here. And the handy thing about diodes and about clipping like this is that actually, if you string multiple diodes like this together, then kind of the zone in which with they are not active kind of expands. So if you had a single diode just here, and then you had 700 millivolts up here, 0 volts down here, then the diode would already conduct a lot of current. But since it's 3 in a row, they are kind of, I don't know how to call this best. They're dead zone, something like this. It just adds up. So normally a diode would kind of start conducting at noticeably at maybe like 250, 300 millivolts. But since we have 3, in series, it's not happening yet. So, but if I now increase the cutoff frequency here, or I turn this knob, so there's more of a current flowing here, and we have a higher voltage here. Then we can actually see in the simulation that there is a current flowing now through the diodes, and this means that they are clipping the voltage, because if they're not conducting, then the voltage at this point is unaffected. But as soon as they are conducting, then they're basically like sucking away or letting some of the current leave this area, and they go, like the current goes to ground and the voltage here drops. And that was my crude little way to make sure, or to try to make sure, that the voltage would not rise above the threshold beyond which the filter would start glitching out. And there's actually, like here in the simulation, there's actually a nice visual way that we can take a look at this. So, and it's very simple. So what we can do is we can take all of this stuff and we just move it away. And just to not confuse you more, I will delete this diode for now. We can add this in later, but for now, let's just get rid of it. And what I will do now is very simple. I will just put an analog output here, so we can see what the processed CV would look like. We can get rid of the filter output. We can get rid of the input signal. And maybe I have a better idea. So no, first what we do is we take one of the CV inputs, doesn't matter which, we get rid of it. And what we do instead is we send in a triangle wave. Now, I'm using triangle waves because, like for me, it's very easy to see if a triangle wave is distorted. With sine waves, maybe I don't have the eye for it, but it's hard to me to really see, like when a sine wave starts to get distorted. So with a triangle, I feel like it's easier. And yeah, what I will do is okay, let me think. So right now we have a triangle that is centered around 0 volts and that is swinging from plus to minus 5 volts. So that would be our CV. Maybe we start with that and see what happens. Okay, so the concept is basically that I will put this one in the scope on the left hand side, and I will put the output of the CV processing on the right hand side in this scope here. And then I should probably bump the frequency up like a little bit, maybe to 200 hertz. And now what I want you to do is basically just look at the way that the triangle is distorted here on the right hand side. I should increase the speed. My laptop doesn't like this. That's annoying. Why is it so slow? Okay, I will increase the scaling here. Maybe that helps a bit. Yeah, that helps. And then also increase it here. Okay, so I'll try to have the same scaling. That looks to be about right. Okay, I will remove the current because we don't need that. We only care about voltage here. Okay, I will need to turn down the cutoff, and I will do the max scale thing here. And I think you can already see like what I was just talking about. Okay, so first thing that I guess stands out is that the bottom of the triangle seems to be unaffected. So we have a nice spiky bottom here. We have a nice spiky bottom there. So this is kind of one-to-one the same. And why is that? Well, because like I explained, our clipping here only affects positive voltages. Because of course, these diodes will only get activated whenever the voltage up here is higher than the voltage down here. So if the voltage here is negative, then these diodes will block anyway, because they're diodes. They're not letting anything through in the reverse direction, basically. So that's why the bottom part is unaffected. But at the top, you can see what I was just explaining. So the effect here is rather mild because, like I said, the input triangle is only going up to 5 volts. And we have a voltage divider in here So this will make sure that the voltage here doesn't rise to 5 volts. Like we're going up to, we can see it down right there in the corner. Looks like something around 1.2. Let's just stop it there. Boom. We're going up to, no, that's not it. Here. Yeah, something like 1.3, 1.4 volts. And this seems to be right, in the area where the diodes start conducting. So that's why we can see that the top of the triangle is kind of being like smooshed a little bit, like it's being pushed down just slightly. It's a bit rounded. But now what we can do is we can increase the volume or the amplitude of this triangle that we sent in. So let's do it carefully. Let's go up to 6 volts first. Let's see what happens. Okay, you can see that the rounding is like, just a little bit more intense. But I would also say that the triangles, this output still got a bit taller. So the point at the bottom, just gets a bit higher still. And now if we increase this by a lot, so let's say we go up to 10 volts, which is, I think my envelope is like peaks out at 9 volts. But let's try it with 10 volts. Let's see what happens. Okay, and there you can see my problem. I mean, keep in mind that right now the cutoff knob is also set to 0. So we don't, there's no added current coming in from our cutoff potentiometer. This is all coming from the CV input. So if I now turn up the cutoff more and more and more, maybe a bit more. Okay, now it's very extreme. If I turn it up all the way, then probably, yeah. Now it's really extreme. So I'm going to stop this, and what we can see here, basically, is that again at the bottom, we still have this is still spiky, but actually I'm not sure if this is because of the scaling, but to me it looks like as if the angle here is much sharper than here. This might also be an effect of the clipping, but the main effect that I would like to focus on is basically what's happening here at the top. As you can see, the trajectory of this rise is kind of very, very strongly affected. So you can see that the voltage rises very quickly at the beginning, and then there's this knee, and then it kind of, it bends, and then there's this very shallow rise and this very shallow drop at the top. And what this does, I mean, first of all, what it does is it clips our CV as we want it. But at the same time, it also changes the linearity of the CV. So, I mean, ideally, what you would want is you would want to have this signal here, like the signal that you sent into the CV input, you would like to have it translated as faithfully as possible to then be used to control the filter, right? Because in effect, like what you hear when you try this, and we're going to look at this later, but or if you build the circuit yourself and you try this, like what you're going to find is okay. So the thing is, and I explained this I think in the main episode. The thing is, oh no, I just explained this like 10 minutes ago. The thing is that the relationship between the voltage difference between this point and the current going through here is exponential. So a linear increase in voltage between these 2 points will see an exponential increase in current flowing through the diodes. And this means that a linear increase in voltage between these 2 points means that the cutoff frequency is rising exponentially. And this is, like with filters, this is just what you want, because I said this many times, but this is just the way that our ears actually work. Like we don't hear volume or is it changes in frequency? I'm not sure, but you know, just for me as a layman, I would say like our ears work on an exponential scale when it comes to amplitude, but also when it comes to you know, frequency perception. And so if we want our filter kind of to sound natural, then what we want is we want it to kind of react exponentially to linear changes in CV. I mean, you could also just build a filter that where the relation between CV and cutoff frequency is linear, but then probably for it to sound right, you would use like just an exponential CV source, basically. But since, I mean, in my rack, like all my envelopes are basically linear. So what I want for this circuit is basically, I want this input signal, like this, you know, you could take this triangle, for example. I want the linearity of this preserved, basically. So the signal that I send in here, I would like it to stay. I mean, of course, it should be downsized, or it should be like properly, like the amplitude should be modulated so that it does work with a filter. But best case scenario, it shouldn't be distorted like this. So this is really what I wanted to avoid. And the problem with that was that, like I said in the beginning, like no matter how much I looked, for some reason I didn't find a better solution. And so I basically just assumed that a proper solution would be hard to do, or would require special components and stuff like that. But in the end, it's extremely simple. It's actually extremely simple. Now the question is, how do I reveal this best? I think I'm just going to show you what the circuit is, and then I'm going to talk about it. Okay, so if we want to use this alternate solution, all we have to do is we have to get rid of this stuff, which is nice because it also reduces the number of total components. Sorry guys, my connection just died. I'm very sorry. My Wi-Fi is terrible, and my router really just likes to drop connections. So tell me if you can hear me, please. Well, YouTube Studio says that there is a connection, so I'm just going to assume that I have a connection, and I am just going to keep talking. Okay, so let's get back to this. So as I was saying, I don't know if you heard what I was saying, so let's back up. So what I just did, let me delete this. Okay, so what I said was that the first step to a better kind of CV processing, CV clipping, is that we get rid of this stuff, which is nice because less components is always nice. Then next up, what we do is, it's very simple. We put a diode here. I have to remember to apply the proper model here, which is this one. And then just for simplicity's sake, for now, I'm just going to use a voltage source here. We're going to have to use a trimmer later, but I mean, this is basically the same thing. Okay. Let me put the output in again. And then let me adjust the voltage here. I think it was, how much was it? I think it was like something like 2.2. Okay, so let's put the output in here. Let's reset this. Oh, this is of course not correct, because this is just wasting a lot of current. We have to put a resistor here. And we have to put a decently sized resistor here. And now we put this as max scale. And yes, so you can see that with just one resistor and one diode, I have actually managed to implement exactly the solution that I was looking for. So what is happening here? Well, first of all, what we can clearly see is what we had before, and explained this in my video, is we had soft clipping. So we had, we didn't have like a hard threshold beyond which the voltage couldn't rise anymore, but it was more like, it was kind of a nudge down. It was like kind of pushing it down slightly, but it didn't stop the voltage from rising. And here what we can see is that whatever voltage I put in here will be the voltage to which we will clip the CV. So right now I put in 1 volt. And so we can see that the output is allowed to rise to 1 volt, but not more. It's just, cut off there. And the cool thing about this is that there's no, like in the line like leading up to the threshold, there's no distortion here. So we have just the nice linear rise, and then we have like the sudden cap here, and then it just stops. And it stops until the voltage drops below the threshold again. And with this, we can like really fine tune. We can really fine tune the voltage beyond which our CV should not be rising. And okay, so now let's talk about how this works, because when I saw this, I thought like, how can that be enough? But yeah, I mean, it's actually very simple. So first, let's talk about a situation like this. So the voltage here is low. So right now we are at minus 112 millivolts. So what happens? Well, this op amp right here is set up as a buffer, right? So what it will do is it will just copy the voltage from here to the output. So here we have, minus 112 millivolts. So at the output, we also have minus 112 millivolts. And that's not sorcery. That's just a buffer. Well, and then what happens? Well, we have a diode here, and we have a voltage here. And right now, the voltage at this point here, so at the op amp's output, is, oh, whoops, shouldn't do that, I guess. Okay. Now it's even negative, but yeah, whatever. So the point is just that the voltage at this point here, so at the op amp's output, is significantly lower than the voltage at this point here. Because, I mean, sure, we have a resistor here, but in the end, that is only going to drop a little bit of voltage here. I mean, of course, the current is flowing into the op amp's output, but still, the voltage here is going to be higher than the voltage at the op amp's output. So then what happens is that there is a current that is flowing, from the voltage source through the resistor, through the diode, and into the op amp's output. And this causes the voltage at this point to drop naturally. But then on the other side of the spectrum, what happens if the voltage here is higher than the voltage on this side? Well, very simple. So right now we have 2.167 volts here. We have 1.2 volts here. That means that the voltage here is higher than the voltage on this side. And this automatically means that the diode will block, because diodes don't allow for current to flow in this direction. They only allow for current to flow in this direction. I mean, of course, there's like leakage current and stuff like that, but generally, if you don't stress your diodes too much, that's negligible. And so basically, like in very simple terms, what happens is whenever the op amp, whenever the voltage at the op amp's output is higher than the threshold voltage that we put in here, then we basically cut the op amp off. So the diode will block, and the voltage here is completely defined by the voltage at this point. So if we set it to 1.2 volts, then the maximum voltage that can be reached at this point is going to be 1.2 volts. And like we saw, or like we can see here, we don't get any distortions. So and I'm not entirely sure. Like I haven't thought the circuit through that much that I can like precisely explain why this diode does not cause any distortions in the output here. But like you can see, it doesn't. Which to me is a great win. So this was exactly what I was looking for. So just to explain what this will do for the filter in the end, this means that the top end of the filter will react exactly the same to a rise in CV than the low end of the filter does. So it will always be an exponential relationship between the CV input and the cutoff frequency, which is super cool. And I also, like I already implemented this, I tried this, and what this means is that on paper, in theory, and also in practice, but not in all scenarios, you can actually get this filter to track volt per octave, right? So you can, if you put it in self-oscillation mode, so if you turn up the resonance, you can actually play this filter like in tune, which is nice. But I mean, of course, there's always a but. The problem is that these diodes are obviously very dependent on temperature, and so the volt per octave stuff really does not last. I tried breathing on the diodes, and that completely threw the tuning out of whack. So we would need some sort of temperature compensation there. But in theory, it would work, which in itself I think is super cool. So when I found this solution, I was very happy. Like I said, less components, it's less messy, it's more precise, it's better. But there's another thing that I was kind of unhappy with, and that is a way simpler issue that I kind of like that was not on my mind so much in the beginning. I just kind of started thinking about this like once I found this solution, and that has to do with how this op-amp is set up, basically. And I think someone also commented about this and kind of told me that this is something that should maybe be changed, because it's a very simple change. So what's the problem? Well, it's very simple. When you use an op-amp to buffer a multi-input voltage divider like this, because I mean this is all that is. So we have one voltage source here, we have one voltage source here, and another one here, and then we have these resistors C in series. And then at the point where they all join, which is here, we have this one resistor to ground. So what this does, or what the problem here kind of is that all of these inputs influence each other. So I hope I can show this. Maybe I deactivate the clipping for now. Maybe this makes it more clear. Right. So we can see our triangle here. We can see our triangle here, and I think what you can see right away, I hope you can see, is like here we have our 0 volts line in the middle of the waveform, because this is properly centered. So bottom half, top half are symmetrical, like above and below the 0 volts line. But then if you look at the output here, you can see that the whole wave is shifted upwards. So the value here is at minus 1.4 volts, and the peak is at 5.5 volts. And now the question is, why is that? And well, I can tell you, it's very simple. It's obviously because of the cutoff. So look at what happens if I lower the cutoff. Like if I pull the cutoff down to 0 volts, then you can see that the triangle basically travels down. And now it's like semi-centered. It's still like a bit below the 0 volts line. And I can probably attenuate that effect if I drop the resistance here the cutoff potentiometer down from 100 to just 10 kilo-ohms. Okay. That was actually not the effect I expected, but it makes sense. Okay, you can see that the waveform actually shrunk down. So let me do this again. Let me push this up. At 100K, the waveform is definitely bigger. And now if I drop it down again to 2K, you can see here that the waveform gets smaller. Well, why is that? It's very simple. That is simply because this path here, going from this point through the 10K resistor to the potentiometer is now basically a path to ground, right? Because here on this end of the potentiometer we have ground. So in effect, what happens is that our voltage that is pushing a current through these resistors now has like two kind of feasible ways to go to ground through. So we have the 47K here to ground, and then we have the 10K here to ground. And also, if you're strict, like we also have another resistance that is going to yet another that is forming yet another path to ground. And so what happens is that this input CV is affected by whatever is applied to these inputs. So if I now push the cutoff frequency up, and let us also push the CV here up. I thought it would actually grow more. Wait, we are now swinging from 7 volts to 10 volts. So that's 3 volts peak to peak? 3 volts peak to peak. Okay, and now look at what happens when we drop this. We drop that. And then we go max scale again. Yes, well, we know we're now at minus 1.3 to plus 1.4. That's still 3 volts peak to peak. That's not what I expected. I feel like I'm talking bullshit here now. Okay, you know what? Let me try this. I will delete this guy. I will delete this guy. There we go. Okay. This is actually the effect that I meant. So now what we have is we now have our waveform that's going from minus 5 to plus 5 volts. So finally, this is what I meant. So now the signal that we feed, which is minus 10 to plus 10 volts, is now divided down by a factor of 2, because we have a 47K here, we have a 47K here, so we have half of the amplitude on the output. So here, minus 10 to 10, here we have minus 5 to plus 5. So it's exactly half. That's what you would expect from a voltage divider. But if I now go back and I add in the other two resistances, which are now going to ground, then that kind of thing is completely out of whack, because we still have minus 10 to 10 on this side, but now we have our, minus 1.5 to plus 1.5 here. So this basically affects, this kind of attenuates the CV that we send in, right here. And this is actually something that is, I wouldn't say it's undesirable. It's, I noticed it while I was using the module, because, if I have nothing plugged into CV2, then like if I just delete it, see an effect here. No, we don't, because the impedance here is much higher. But in my circuit, I actually noticed that like whenever I did connect, it would kind of affect the CV response. The envelope that I was sending in made the filter sound different than it did once I plugged in the other CV input, even though that other CV input it was just sitting at 0 volts. And that doesn't really feel right. Maybe it does feel right to you, maybe it does sound right to you. in my case, I thought like, this is not ideal. Like I would like the cutoff point to not be really affected if you send in a second CV signal that is sitting at 0 volts. That was just what I was thinking. Okay, let me know if this was too confusing. I hope that made sense. So, what is the solution here? It's extremely simple. So, and actually, like, I feel like I very often read the people say you should try to avoid using op amps in the non-inverting configuration. And I've seen various reasons, and none of those like really convinced me ever. So I just kept using my trusty non-inverting op amps. But in this situation, yes, the solution is very simple, and it is to use our op amp in the inverting configuration. And I will explain to you why. Like, we can see it in the simulation in a second. So it's very simple. So what I need to do is I need to take this op amp. I need to delete the connection between the inverting input and the output. And I shouldn't delete the op amp while I'm at it. And then what we do is we send our mix of CV signals into the inverting input through a resistor. And now I have to remember what I used. I think I used a 100K. Well, we will see. We have to then ground the non-inverting input, and we have to connect the inverting input and the output through a resistor. And you might ask, why are you not using the same values for these two resistors? Well, because if we use an op amp in an inverting configuration, then we can actually use that op amp to reduce the amplitude of our input signal. That's something that's not doable with a non-inverting op amp. If you have a non-inverting op amp, you can only have a gain of 1 or more. So you can only increase the amplitude of a signal. With a non-inverting op amp, you cannot reduce the amplitude of a signal. With an inverting op amp, you can. And so what we can do is we can get rid of this resistance to ground, basically. Because what's happening now, I mean, I guess most of you know this, but if you set up an inverting op amp like this, and the input resistance is higher than the feedback resistance, then you have a gain that is less than 1. So in this case, I always say that it's 10%. It's not 10%, but it's in that ballpark, somewhere around there. So let's just reset this, and then we will see what we get here. So we still have our minus 10 to plus 10 volts input triangle. And I have the cutoff. I should set it to, yes, to ground. I will recalibrate this resistance here. And now we can see that what can we see? Well, that we have, I think I should remove this thing because it's kind of misleading, no? I don't know if it had any effect. I guess it didn't have any effect, but yeah, let's compare what we have now. So we have our minus 10 to plus 10 volts input signal, and on this side we have our, what do we have, like about minus 430 to plus 430 millivolts signal, which is actually too low, I would say. So what we want to do is we want to probably drop the input resistance here. Let's see where we're at now. Okay, so now we go up to 400, to 750. It's still a bit low for my tastes. So let's drop this to 4K7, which would also increase. No, it would decrease the gain, sorry. So we increase this to say 20K. And now we are at 1.5 volts. That looks better to me. Because keep in mind, I mean, what we're looking for here, like we're looking to clip our CV, like in the end, we want to clip our CV at something around, in the videos, I always said 1.2 volts. That's not entirely accurate. Like when I was really like trying it precisely, it was something around like 1.28 or 1.29 volts, something like that. Like that was like right below where the filter would glitch out. So if we have 1.5 here, then that's probably kind of, then we have a bit of overhead here, which is nice. Okay. And now for my big trick, like with the last example you saw, once I deleted the resistance here that was going to ground, it had an effect on our processed CV. So, by taking out the resistance to ground, we saw that the scaling or the amplitude of our output signal would change. And now what we're going to do is we're going to try and remove these. And I hope to God that this won't affect the output, because then I've been talking trash for 10 minutes. Sorry, let's see. It does affect it. That is kind of embarrassing. I'm very sorry. I really thought, I guess I should have tried this before. I really thought that this would mean that it does not have any effect on the input CV. But apparently it does have an effect. Let me check the chat if you're already eviscerating me. Is it possible to implement a similar solution for the resonance voltage limiter too? We could actually try this. I haven't thought of that. We could try that. Wow, I did not expect you to follow through with my suggestions to sample transistor. Yes, actually, yeah, you did suggest that. I remember. Yeah, that was actually where I got the idea. So thanks. Why the extra 100K resist? Yes, that's the reason. That's actually the reason. Thank you. That's why that doesn't work. You need to make use of the virtual ground on the inverting op amp. Yes. Okay, I'm just a bit nervous, guys. I'm very sorry. That's why I messed this up. So, of course, this resistance here is nonsense. Because in the inverting configuration, what you do is you take all your CV sources and you connect them directly to the inverting input, through their resistances or through their respective resistances, and the value of the resistance will kind of determine kind of the presence in the mix, something like that. Maybe sounds okay. Okay, so thanks for the suggestion. Let me try this. We'll send this in. We will send this in through our. Maybe let's make this look a bit nicer. Boom. Pull this away a bit. And then we pull this down. Like that. Perfect. I'm just going to take out the attenuators here. And we're just going to go with straight resistances. So let's just weigh them all evenly. So let's just go with 47K on all of them. Like that. And then, oops, that is not enough. We have to go to 47K. Okay, then we connect all of them. This is a bit off, like this, okay? And then we send them into the inverting input. And now we should see what I wanted to show. Okay, cutoff knob is set to 0 volts. These are both set to 0 volts. Okay, what do we have? Well, we have minus 10 and 10 on this side, like before, and now we have on the output minus 4.2 and plus 4.2. Okay, and now we will do the same thing that I just did, which is deleting these resistances, and let's see what happens. As you can see, nothing happens, and this is exactly what I wanted to show you. So thanks for the tip. Who said it? Phobos. Yeah. Thanks a lot. Perfect. Any more questions? Any chance of trying this filter with different diodes than LEDs and 1N4148s? Germanium, silicon, Zener. Maybe using light from filter bright enough to control some LDR compression. The problem is I don't have. I'm like I wanted to buy those like special kinds of diodes, but I don't have any. The only ones that I have are rectifier diodes, and I don't think that they are going to sound interesting. Let me know if you still want me to try them. I would have to see if I have enough of them. We could look at this in the end for sure. You should connect your summing net. The minus. Yes, that's what I did. Why are you nervous? You know more than 99% in this chat. I would doubt that. I think my strength is actually just trying stuff or like throwing shit on the wall and see what sticks. So I guess like on the theoretical side, there are many people that are better equipped than me. But thanks for the compliment. Help me. Why am I so bad at electronic designing? I mean, you just saw that I'm also not the best. So just don't get bogged down. Try it. And most important of all, what I found is you need something that you want to do with it. So if you're just trying to get good at electronics for the sake of being good at electronics, I feel like it's not going to work. At least it doesn't work for me. But as soon as I have a goal, like for me, it's building synthesizers. As soon as I had that goal, like it just worked because I always knew what I wanted to do with it. So maybe that's any help. Okay, so let's go back to the simulation. Okay, so this was a big success, and you saw what I was trying to describe to you. So now it doesn't matter if we send in 0 volts here or not. The output of our CV processing will be unaffected. So this is what I wanted to do. But now the question is, what does happen now if you increase the cutoff voltage or the cutoff knob? You turn the cutoff knob. So let's see. Okay, so you saw that the triangle was going down, which some of you already noted in the chat. Like the problem that we're going to have to solve is, of course, this op-amp is inverting. So whatever voltage we send in here, what we send in here on this side, we're going to have the exact inverse of it on the other side, which is not good because we want our filter to open up when the CV increases, and we want it to close down when the CV decreases. So this is something we have to worry about in a second. But what you can see now is that what happens is that the entire waveform is moving down. So the center has now been shifted downwards, which is nice. Might have been confusing earlier because I was talking about that. So just to reiterate, so what I want to achieve here is, maybe that's in simpler terms. Imagine you set the cutoff knob to 12 o'clock. And let's say 12 o'clock is exactly 10 kilohertz for the cutoff frequency. And with my old implementation, if you then send in a CV input that was like somewhere below those 10 kilohertz, like it was at a CV, what was at a voltage that translated to cutoff frequency was below 10 kilohertz. In my previous implementation, this would have pulled the frequency down. So it would have taken the frequency from 10 kilohertz down to like whatever the CV was able to pull it down to. So if you had a very negative CV, let's say minus 10 volts, then it would be able to pull the cutoff frequency way down. And this was kind of the behavior that I wanted to circumvent, that I didn't want to have, because what I want to have is I want to be able to set kind of the base cutoff frequency that we're dealing with, and then that should kind of be the base frequency that we're working with, from where we are applying this CV. Kind of. I'm just realizing that this is very convoluted. I think maybe I guess you all know this. Like when you use your filters in your system or on your synthesizer, this is usually how things work. You know, you set the cutoff knob, and then you send in the CV, and then it modulates the frequency from where you set the cutoff knob to. That's just all I want. That's what I want to achieve. And with this kind of configuration, this is exactly what you get, basically. Okay, but onto our problem with the inversion of the CV. So, like I said, our problem now is that whatever voltage we have at this point is going to be inverted here, and we don't want this. We want a positive CV to have the effect of raising the cutoff point for our filter. And right now, if I were now to just connect this guy back up to our op amps, then we would have the inverse effect. And probably I can just show you this. Maybe that would be more clear. So all we have to do is we have to connect this guy to this point. And then what I'm going to do is I'm going to show you the CV input. I'm also going to show you the filters output. And then we're going to run this. And it's painfully slow. So let me adjust the scaling here. Okay. And should probably also adjust the scaling here. And still painfully slow. So let's increase the speed. We don't need the current. And as you can see, our filter is just permanently blocking. And of course, this is because our op-amp's output here is constantly negative. So our diodes over here, whoopsie, our diodes over here are all blocking. So there's no current flowing, so you don't get any meaningful output on the filter's output. So what I have to do is I have to pull the cutoff knob in the opposite direction. And I guess we have to also decrease the frequency of this input or CV input oscillation so that we then maybe get a better look at how this works. This is still too fast, I feel. I think we still have to drop it down a bit. And let me bump up the speed again. Okay, it's a bit crude, but I guess you can see it. So whenever the triangle here on this side is above the 0 volts line, then our filter is dead. And whenever it is below the 0 volts line, then our filter opens up. And this is exactly backwards to what we want to achieve. We want to have it the exact other way around. So whenever the CV is positive, we want our filter to open up. Okay, so what can we do? Well, when I was working on this, I first thought, now I have to use another op amp to invert it again. So that was like my first idea. Just take another op amp like this, set it up as an inverting buffer, so with a gain of 1, and then send that to our op amps. And now you might ask, like, why not? Like, why not use another op amp? What's the problem? It's very easy, actually. So if we just count the number of op amps that we're using right now, we're using 1, 2, 3, 4, 5, 6, 7, 8. And 8 op amps fit perfectly, or are perfectly, no, what's the way you say this? If you use two TL074 chips, you have 8 op amps because there's 4 op amps on each chip. If you want to use 9 op amps, then you have to use another chip. You have to use another TL071, I guess. I think they exist. And I really wanted to avoid this. Like I didn't want to add another chip. And so I was kind of bummed about that, and I thought, like, annoying. I don't want to add more to the bill of materials. But then I kind of thought, wait a second. We don't have to use another op amp, actually. Because as you might remember, well, the question is like, what are we using these two op amps for? Well, the first thing, of course, is they are picking up our input signal from here. You know, we're sending our input signal into both of these op amps, and they are basically just buffering it to then for us to then be able to apply it to the bottom and the top here of the diode string. But what they also do is they mix the oscillation with the CV, and this guy here is taking in the CV as is. So it's taking in whatever it's being fed through here, and it's adding it to the oscillation. So if we send in 1 volt here, and we have our oscillation here, then what it's spitting out is basically just the CV plus the oscillation. And this guy down here is doing the same thing, but it is inverting the CV. So what this guy is doing is it's taking the oscillation and it's adding it to the inverted CV. So if we apply 1 volt here, then this guy says, okay, 1 volt, that means minus 1 volt, and then plus the oscillation, and then it applies it to the bottom of the ladder. Okay, so the trick here is that we just switch these two op amps. Like, they just switch positions, because this guy's inverting the CV anyway, and this guy is using it straight up. So if we have a negative CV here, say we have minus 1 volt as a CV input, and these two guys switch positions, then this guy, which is now up here, will invert the CV. So it will take minus 1 volt and make it into 1 volt. And this guy, which is then down here, will just take the CV straight. So it will just take the minus 1 volts. And boom, we have the same outcome as before, without having to use another op amp down here, which is a win in my book, I would say. And because I'm now, I think, am I too lazy? No, I'm not too lazy. Okay, so let's just take these guys. Whoops. Take these guys and move them around. Boom. Now we shouldn't move the label, I guess. So let's take these guys too. Move them here. Don't forget the ground connection. This one goes here. And then what we do is we connect this simply to the bottom. And we take this guy and we connect it to the top. And then we have to watch out a bit because these connections are way too long. Let's shorten this guy up too. Okay, let's make it nice and symmetrical. And now all you have to figure out is which connection goes where, obviously. So with this guy, it's very easy because this guy feeds the CV and the oscillation into the same inverting input. So all we have to do here is, let's be a bit neat about it. We send our oscillation in here, and then we also take it. And for the other op amp, we also have to send it into the inverting input. So boom, it goes in here. And then these two inputs, they need to connect to our CV. And now, of course, what we also have to do is we have to put in our clipping again, of course, because I mean that was also the point of the whole thing, right? So what I'm going to do is I'm not applying the exact same solution, because as you might remember, like before, we were clipping to a positive voltage. You can still see it down here. We were clipping the CV at 1.2 volts, at positive 1.2 volts. But as we have set this up now, we are not dealing with positive CV mostly anymore. And this threshold beyond which our filter is glitching out is now not at plus 1.2 volts, but as at minus 1.2 volts. Because remember, we inverted we switched positions. We switched the positions of these two op amps, which means that the usable range of our CV is now basically from 0 volts to minus 1.2 volts. It's exactly inverted. So we don't want to clip the CV to a positive threshold, so not to 1.2 volts, but actually to the inverse of that. So to minus 1.2 volts. And to do that, we will have to also invert the position or the orientation of our LED. So if you remember, what we did before was we connected our LED up like this. Because what happened before was basically that we wanted to make sure that whenever the voltage here, at the op amp's output is higher than the voltage on this side, then we wanted the diode to block. But now what we want to do is we want to make sure that the op amp doesn't go more negative than the voltage on this side. So that's why I have to invert the orientation of this LED. So now what happens is if the op amp's output goes lower than the voltage at this point, then the diode will also block because it resists any current that is going in this direction. It only lets current flow through it in this direction basically. We can just try this out. So let's run this. I will need to put in another output here. And maybe increase the frequency so we can see better. That's too fast for my laptop. Okay, but yeah, as you can see now, we are clipping the CV to minus 1.2 volts. So it's not allowed to go below that. Anything above that is fine. Anything below that is a no-go. So this is exactly what we wanted. So I'm going to go into the chat now and I'm going to ask you if you have any questions because I feel like this was a bit convoluted maybe. So let's see what you wrote. Could you also change the direction of the ladder diodes instead of switching the op amps? Pretty sure yes. Yeah, of course. I mean, why not? Of course you could do that, sure. Just felt that switching the op amps around was maybe a bit faster in the simulation. But yeah, of course. There's also a trick to limit the CV voltage by using Zener diodes in the feedback loop of the op amp. Haven't heard of that. Maybe if you can post a link or something, that would be nice. Who else thinks Dave's content changed quite a bit over the last months? I don't know who David is. I guess you were talking about something that I didn't see. Is it true that if you put a resistor on the wrong way around, then the electrons drop out? Probably. I missed those teardown actions. I don't know. Okay, so I'm assuming from the chat that there's no confusion, I hope. So let's just go on. If there's something unclear in the end, then we can still talk about it then. Okay, one final thing. This is another vague thing that I'm going to tell you. You might ask why I am not putting another diode after the output here, because if you remember, like if you think back to my video on the filter module, I explained that there was a problem, or that I thought there was a problem with the situation where these diodes are reverse biased. So if I connect this here back up, then we should actually be able to see this in the simulation. So let me decrease the speed. Okay, so you can see here that whenever the CV is going very positive, then you can also see that the op amp here, the output goes very negative. And that's what it means when it goes red, basically, these lines. And At the same time, this means that the op-amp down here, because it's always doing the inverse of what the op-amp down up here is doing, this means that the op-amp down here is going very, very positive. And if we have a very negative voltage here, a very positive voltage down here, then this puts our diodes into the reverse biased mode, which means that they are blocking. And if you remember what I showed you in the video, I had this problem that whenever the CV was going, was kind of switching polarity very fast. It was going, like in the video, was going from negative to positive very fast. Then we had this clicking noise on the output. And I was assuming that this was in some way related to the moment when the diodes are, going from reverse biased to going forward biased. So from whenever they are blocking to whenever they are letting current pass through them. And last week, I think it was last week or the week before, I did a live stream where we built a VCA that is based on this idea. It uses the same idea, but just for amplification purposes, for VCA purposes. And in that stream, I was running into the same problem, naturally. So this horrible clicking noise, and I was doing the same trick that I did in the video, which was basically just, in our case now it would mean putting a diode here that only allows negative voltages to pass through. So now whenever this goes positive, the diode here will block, and this means that our diodes will never be reverse biased, because of course if the voltage here never goes positive, then the voltage here will never go negative, and that means that the voltage between these 2 points is never going to be reversed. So there will never be a higher voltage here than here. And in this video, this worked. And also in the live stream that I did on the VCA design, this also worked. But then someone suggested that instead of putting the diode here, I could also just get rid of this resistor down here. So that's what I did in the stream. I set the VCA up like this. I got rid of the diode here, and lo and behold, it actually eliminated the clicking noise. And so afterwards, I tried this with the filter. So I did the same thing that I just did. I removed the resistance here, and wouldn't you know, it also eliminated the clicking noise. And I think the person in the stream said that it has something to do with the I don't know what the word was, but maybe we can see it here. So yeah, you can see here that whenever the filter is closed, so whenever our CV here is going negative, you can see that the output voltage kind of stays where it is. So in our case here, boom, now it's hanging at a positive voltage, and now it's it's filtering again, and now it's hanging at a negative voltage. And I think I have to look into it more, but I think that maybe let's try it. Let's see what happens if I now add in the resistor here again, the 2K resistor, if we see any change here in the simulation. It looks the same to me. But from what I gathered, like the idea in the stream was that taking out the resistance in some way makes the switching, from going from this this kind of stationary voltage back to the oscillation, maybe less abrupt or sudden. I don't know why. This is just me talking out my ass. So if anyone knows in the chat, then please tell me. But yeah, just from the same talking from the same attitude of throwing shit at the wall and seeing what sticks, this stuck. So this eliminated my problem. So that's why I went with eliminating the resistance here, and also taking out the diode here, because like I said earlier, I like less components. I like less complex layouts. That's why I decided to take these out, because in effect it had the same effect. So that's why I did this. And that is basically all when it comes to the changes to the filter design. So what I would say now is I'm going to get out the breadboard. I've already set this circuit up, and we're going to play around with it a bit, and I'm going to show you just on a practical level how this works. So let me switch over to the camera. Oops, it's crooked, I'm sorry. I received some OA95 germanium diodes yesterday. I have to put them into that ladder. What would be the expected outcome? I'm actually not sure. Maybe someone else in the chat can say something. Yeah, it depends on the forward voltage. I mean, like, we're going to see with the diodes also that also the kind of resistive range, if you can call it that, of the diodes is going to play a role in what the outcome is going to be. So we're going to see with the diodes, we will have to significantly boost the voltage that is going through them to get them to work at all. So yeah. How important is DC decoupling? I noticed most circuits online have it, but yours don't. Are you talking about like actual decoupling? You know, putting capacitors on the chip's supply pins, or are you talking about AC coupling right now? The curve around VF has a different shape in addition to different forward voltage. Oh, that's about the diodes, yes. Can I ask you a question about your VCO? I built it, but after tuning it and inputting 0.083 volts and 1.083 volts, it jumps 2 octaves instead of 1. Did you tune it? Like I mean, I guess you saw this in the video. What you have to do is you have to use the trimmer potentiometer to adjust the tuning. I think I show this in the third video in my series. You have to take a reliable CV source, and you have to make it jump between 0 and 1 volt, and then you turn on the tuning potentiometer until it's exactly right. So you have to make sure that it's 1 octave, and then it should stay that way over multiple octaves. You can then try to tune it between 0 volts and 5 volts, but yeah, that's what you do in the end. And then you have to like really fine tune it until you get it right. So the circuits are a bit like the power supply unit, with caps going from negative to positive to ground before the lines go to the circuit. The difference is they use lower cap values. Yes, exactly. That's decoupling caps. I don't have them in the file set. I don't show them on my sheets as well. But whenever I actually build a circuit, I do use them, and I can prove it to you. Give me a second. Okay, so here is one of my filter modules. You have to forgive me, I haven't cleaned the flux yet. But you can see here, up here, and then here on this side, you have 100 nanofarad capacitors, which are ceramic, and these are like really directly next to the power supply pins of the op amps. And what they do is they basically eliminate high frequency noise on the power rail, because that would otherwise like creep into your signal, and then you would have noise in your signal in the worst case, if your power supply is noisy. And by adding these here, you can minimize that actually. And if I guess you were also asking about the size. So the question is like, what kind of noise do you want to eliminate? So if the noise you want to eliminate is very high frequency, then you should use lower caps. And the kind of go-to value that you always see is that people tell you to use 100 nanofarads. That seems to be like a good, one-size-fits-all thing for synthesizer modules. But you should also use, or you could, I think it's also good practice to use, like I've used 10 microfarads here, electrolytic caps on the positive and negative rail. and these are more about, I think they're more about like the ground hum, like low frequency noise. To be honest, like the problem with this layout is that in the original thing, I can show you. So in the original thing, I've chosen like a ridiculously small footprint. I guess you can see it here. So the two holes for the 10 nanofarad capacitor are so close together that it was a complete nightmare to solder this in. So for all subsequent builds that I did of this, I just left them out because I couldn't tell any difference. Like I tried leaving them out, I put them in my rack, it was fine. So if you're in a pinch, I guess you can just drop these. But generally, I think it's good practice to also have these. So yeah. Next question. There's also a very neat formula called the Shockley diode equation, which you can input some parameters to determine how the diode's current increases with voltage. Yeah, that's I guess it was about the germanium diodes. So yeah. How important are they and why? I think I just explained this. If you have more questions, then ask. It's so pretty. Thank you. Glad to hear. Yeah, they also must be ceramic or in some case film to work probably. Yeah, I heard that ceramic are best for decoupling, so always use ceramic. Do you still put 100 nanofarads across plus and minus? I read that for op amps, it's sufficient to have 100 nanofarad from plus to ground and then another from ground to minus. I read that adding another one from plus to minus is not necessary. Maybe your mileage may vary, but yeah. Next question. I have a module with a bunch of PWM LEDs and it needs a lot of decoupling to keep from making noise in the case, like around 470 microfarad. Oof, that's crazy. Yeah, of course. Like if you have PWM in your case, that's like a big source of noise, definitely. Like all that fast switching, that's kind of poison, I think. Yeah, it's common practice to put 100 nanofarad ceramic and 1 microfarad electrolytic in parallel. Yes, exactly. There's lots of debate about that. I always put my decoupling across the rails, but sometimes people get mad at me for that. Yes, that's also what I read. That's why I went with the solution that I went with. But like with all of these things, I think in the end it's about the end result. So if you're happy with how your circuit sounds, it's fine. So yeah. Will you try SMD PCBs or stick to through-hole? I said on some videos now, like I'm planning right now, I'm in the process of setting up a shop. So I would like to sell like different stuff to you guys. So first I would like to sell just basic kits, just a breadboard and all the components that you need for, the VCO, for example, so that you can follow along with the videos. This is mainly for people that have trouble sourcing parts. I mean, I guess most of my community, most people are able to buy their stuff, but I feel like there's a lot of people that are kind of scared away by the prospect of them having to go maybe on multiple web shops and like buy all this stuff. And there's like this jungle of components and it's very hard to figure out what you need. And I thought maybe it's a good starting point for people if they can just go to my site, buy a kit, have all the stuff that they need, and they can just set the circuit up, don't worry about it, make it work. So that's one thing that I want to sell. Then also, of course, just PCBs and front plates. That's another thing. And then also kind of complete kits, which would mean PCBs, front plates, components, and interfacing stuff, potentiometers, but also the knobs, because I feel, of course you can always do what you want with my PCBs, also with my designs, no question, but I put some thought into the combination of the coloring of the front plate design of the knobs, and so if you want the complete package, then that's what you could buy in the end to build your own of these. And then to answer your question finally about SMD. So my reasoning is when I sell kits, so when I sell these as a kit, I would prefer to sell them as through-hole, because from what I gather is that most people are comfortable with soldering through hole, and especially people who have never soldered before. I think it's a good starting point to be able to do through hole. But like then, I mean that is not first priority. But then what I would also like to do is also sell assembled modules for people that really don't know how to solder and they don't want to learn to solder. And for exactly this, I'm thinking about going SMD and trying to find like a manufacturer that can do that for me. Because at first I thought that I'm just going to build the modules myself, but then when I kind of thought about it, I realized, I mean, putting together a module takes me, I don't know, like right now 5 hours. And of course that would get faster as time passes on, but to be honest, I feel like I have better things to do, as harsh as that might sound. But because like every 5 hours that I spent on soldering, I can't spend on writing a module, writing an episode, or coming up with a new circuit. So yeah, to answer your question, that's like in that case, I would go with SMD for the pre-assembled stuff, basically. Okay, so there's a lot of stuff. Let me see. You can always put 100 nanofarad across the rails and also from power to ground. That's true. Generally, large capacitors should be placed across the power, close to the input. Small capacitors close to the chips. Exactly. Yes. Like the way I reason about it is, I mean, the big capacitors, like the 10 microfarad that you use, I kind of think of them as like backup batteries. You know, for them, speed is not that important, so they can be further away from the chip. Like I think of them as kind of a reservoir at the power input, like where you kind of build up a bit of emergency charge, basically. Okay, next question. Do you recommend 4-layer PCBs for EMI compliance, even if a 2-layer layout might be enough to be certain that ground loops and other noise sources won't exist? I can't help you there. I'm not that deep into PCB design yet. As you can see, for this one, I went with just one, two layers, just front plate and then the board. To be honest, I like this kind of design because it's simple, it's easy, and my focus right now is on this being easy to build for people. I'm not focusing on making it as small as possible. There's another reason for that. I don't like super fiddly stuff, so that's why I like this to have like a bit more room. But yeah, in general, I want to keep this as simple as possible so that assembly can be done by anyone, you know, by beginners. There used to be a way to cut down cost of PCBs. You add all the caps you think you need, then you take a pair of snippers and cut out caps one by one and see if it's still okay. Sounds like a good plan. That would be exactly what I'm looking for. I think you mean the kits. If so, then great. Happy to hear. If you're a hobbyist, why are you worrying about compliance? True. Probably, yeah. I mean, I guess if you're starting to sell stuff, then that will become important. I guess that I might have to put up with that as well. But for now, I'm not worrying about it. 4-layer PCBs are usually not necessary unless you're working with super precision equipment. You were talking about, I thought you were talking about like a 4-layer sandwich. So 4-layer PCBs. Okay, I'm way out of my depth there. So I'm going to let you guys figure that out. There's a bunch of questions here, guys. Yeah, through hole, since I can reuse components from my breadboards, not having two stocks. Yeah, same. I also feel that it's just nice to have kind of have it translate directly. You know, you take a component off the breadboard and put it into your module. That's a nice thing. So are you full on switching to Eurorack then? For now, yes. I think long term I'm also going to do some stuff for my Cosmo rack also, you know, with PCBs. For now, I'm doing Eurorack, yes. But I mean, you guys can always kind of determine like which direction I go in. So if you tell me that you also want modules in Cosmo format or kits in Cosmo format, then let me know, and I'm always happy to do that. And as I get better at making PCBs, I think I will also get faster at putting out stuff. So yeah, my idea is that 4-layer PCBs is overkill in most cases, but I see so many people using them that I don't even know what to trust. I feel like this is often a general problem that you, or that's a problem that I often have, that I'm aware of certain things that people say are must-dos or stuff that you have to have, but I'm often confused because I'm not sure like why, and that's often because in my specific situation I don't need it. So I mean, I feel like oftentimes there's kind of a clash between the requirements that you have for synthesizer stuff and then for stuff like, digital processing. If you're working with microcontrollers or like more advanced stuff, of course, for that kind of stuff, you're going to need more precision, less noise, all that kind of stuff. But for what we do here, I think we have the advantage of being able to decide with our ears. So if there's too much noise, it's not going to break the circuit, it's just going to sound different. And then if you say, okay, I don't like the way this sounds, then you can look stuff up. That's kind of how I came to decoupling, because I read about decoupling a ton before. I always wondered what it was, why I should worry about it, didn't do it. And then at some point I built something, it was very noisy, and then I was like, that's why I need decoupling. And I would advocate for that kind of approach. Just implement the stuff that you need. And if you run into a problem, you will run into it anyway, and then you can find a solution, and then you know what it's for. So that's what I would say. Unfortunately, in the EU, you need the CE marking regardless in order to sell your stuff. Yes, that's what I meant. I think I will have to worry about that too. You should also sell build modules that use SMD. It's one thing to play with a soldering iron, but you should promote your designs as worthy of anyone's. Yeah, that's what I meant. But I would outsource that to another company, because I don't want to be sitting here in my room and soldering all day and night. That's not something that I enjoy so much. You are a good man. Thank you. I'm glad to hear that I'm a good man. More questions? Any more questions? You should also poll crowdsource suggestions from your audience, but what original modules would make sense to design. I will definitely do that. Just as a teaser, like the next thing that I will do, like PCB and Eurorack related, is because a lot of people asked for me explaining how the PCB design process works. And so what I figured I would do is I'm going to take my VCO, which I have right here. So this is actually, I think this is a version with the triangle output. So what I'm going to do is I'm going to cut this like way the hell down. So I'm going to do just one waveform, so just sawtooth. I'm just going to do one CV input. I'm just going to do one tuning knob, and that's it. And I'm going to go like step by step through the process of designing the board and then also designing the panel. And like I do cut this down so much because first of all, I like simplicity, I like minimalism, and I think just making like one like very small tiny VCO could be nice. I mean, maybe as a test oscillator, something like that. Also, I think it's a good way to explain this stuff. And also, I think it's a good project for beginners to solder. So when those are coming in, I think that would be like a very nice starting point for people who want to learn how to solder. So that's the next step that I will take. And then after that, definitely I will kind of do polls more on Patreon, maybe also here on YouTube, to ask you guys what you want to have. And then on the video front, my current plan is to do an envelope generator next, because in a previous stream, that's what most of you guys voted for, what you want to see. So that's next in the pipeline, actually. Okay, I think the layer count depends on your circuit. For digital stuff with fast switching, 4 layers preferable. 2 layer is fine for pretty much all analog stuff. That's what I meant. I think I think that's a classic example of, you know, we don't need the precision. We are not doing rocket science here. We're just making music. So let me see what else. Okay, I'm going to have to skip on some comments, otherwise you're never going to get anywhere. So let's see what we have here at the bottom of the list. Cosmo rules. I would happily buy a Cosmo kit. Yeah, I must say I also like the bigger. I like the bigger jacks. I like the bigger interfacing elements. So I won't abandon it. I promise. I sold a SMD all the time, and it's not that hard. I've heard that a bunch of times. Yeah, maybe I should try it someday. I will see. What else do we have? Can you do a PCB design stream? Like I said, I'm going to do a PCB design episode. We can also, of course, do a stream because I always need streaming topics. So maybe if I don't have anything else, we could also do a stream additionally to the video. You should play around with the 555 timer. Yeah, in a previous stream I said that I don't like the chip, but then people were kind of swaying me on it, so I will look into it soon. Second, the suggestion for a PCB stream, KiCad if possible. Yes, I have to get into that. For now, I've been using EasyEDA, and I would like to use a better tool because it's a bit annoying to work with, actually. What are the aluminum knobs you're using on your modules? They are from a company called RS Components. I think they operate worldwide, so you should be able to find their stuff in the US and everywhere else. And that was all. Okay, so let's finally look into the circuit. So here I have set up the filter already. So let me zoom in a bit so you can see better. I should make this light a bit brighter, I guess. Let me bump that up. Oh, actually it's already at maximum. Well, I hope it's bright enough. Let me know if not. Great, okay. So I implemented all the changes that you just saw and that you heard me ramble about. A lot. And I don't know if you can see this, but I can immediately see that the board is less crowded. So we have less of a resistor mess here. This is just because I eliminated the 2K at the bottom of the ladder. So now we only have 4 resistors here, and they can be organized in a nicer way. So this already makes the breadboarding way more enjoyable. So that's a win in my book. And then the next thing you're going to see is, like I used to have these 3 clipping diodes here at the back. They're gone too, so also tidier. And then I guess like the biggest thing is that you have this trimmer here, which I added. So if you think back to the schematic, you remember that to set the threshold beyond which we were clipping, I used a voltage source in the simulation. Here on the breadboard, I'm using a trimmer, which I have connected to ground and to the positive rail, and this allows us to set to ground it to the negative rail. So this allows us to set any voltage between 0 and minus 12 volts. And we use this to set up the threshold beyond which we are clipping the CV. Okay. So the first thing that we'll do is I will hook this filter up to my interface so that you can hear something. This is the output. Okay, and then we will also need power. And this is interesting. Like earlier, when I tried this circuit, I plugged in my power. Ooh, that sounds angry. Sounds even worse. Interesting. My power supply is not even on. Okay, so once I ground it, it's gone. But yeah, what I was talking about earlier, when I was setting up the circuit, I connected the ground connector here on this side of the breadboard, and as you can see, I need ground on both of these rails, like on this rail and on this rail. And I've connected them over here, with this jumper. And when I used the circuit like this, it didn't matter to which setting I set this potentiometer. The resonance was just squealing away anyways. So let me show you. Maybe you can hear this. I hope it's not too loud. Okay. No, it's actually gone. Interesting. Because then I fixed it by putting or by plugging the ground in here. Apparently it's not a problem anymore. But yeah, what I just wanted to say is apparently it's a big difference if you plug in the ground here or there. So always think about that when you're breadboarding. Like that might actually be the source of your troubles in some cases. In some cases with noise, or also like if stuff is kind of cross-modulating, it can always be that the ground rail is not the ground rail, like simply speaking, because if you plug it in here, then I guess like if it's 0 volts here, then it doesn't necessarily mean that you also have the same voltage here, because there's so much space distance between it and so much copper or whatever is in this breadboard, and then all the other signals that are feeding into ground. So always think about that. Like if you have trouble with your breadboard, always think about this kind of stuff. Okay, so let's send in an oscillator. Okay, and I have already fine-tuned this trimmer to properly clip RCV. So right now you will hear the end product, like how it's sounding when it's working well. Whoops. Okay, I forgot to plug in my synth, which is stupid, but yeah. Let's see. Okay, so if I turn up the resonance, then we should be able to judge better like where the cutoff frequency exactly is. So very low. And now it's very high. And if I turn it up even more, the resonance, then I guess you can hear, like if I now turn the cutoff frequency up again, like way up, then I guess you can hear a point where the resonance just disappears. I mean, I'm already over 30, so for me it's probably way below 20 kilohertz. But before, like in my old implementation, you could not push the cutoff frequency up high enough for the resonance to kind of disappear, or to get so high pitched that that you can't hear it anymore. So let's go up again. So this for me is where the resonance disappears. There it is again, now it's gone. There it is again, and now it's gone. And I can go even higher. So this is already nice because now, the cutoff knob is able to open up the filter completely. This is something that did not work before. Like before, I had the problem that the cutoff knob would kind of top out at something around 10 kilohertz. And this is kind of already dealt with now. And now I'm going to show you what happens if we mess with this trimmer here. If I can find my screwdriver. There it is, perfect. By the way, I think I got this screwdriver in some kit, like, with some multimeter. And I must say, I've never seen one like this before, but it's so handy. I mean, you can just swap out the tips, and you have, like, you know, now I have a Kreuz, and now I have a Schlitz, which is amazing. Maybe there's something very mundane, but I really like this thing. Okay, so what I'm going to do now is I'm going to turn this cutoff potentiometer way up, and then I'm going to mess with this trimmer, which, like I explained before, is going to change the threshold voltage to which we are clipping the CV. And I guess you can then hear what happens. Just to precondition you, when we drop the voltage down, or the threshold voltage down, the maximum cutoff frequency is also going to drop, and if we push it up, then at some point the filter is going to glitch out. So let's see. Okay. Weirdly, it's not glitching out anymore. Maybe this is something to do with the 2K resistor that I removed from the bottom. But you can hear that the sound is getting quieter. Now we'll turn it in the other way, and the signal should come back, I guess. Yeah. And if I keep turning, we can lower the cutoff frequency. Okay, so what I'm doing right now is I'm lowering the threshold. I'm pulling it way, way down. And now what's happening is our cutoff potentiometer is set to full blast. But the clipping basically says, no, you don't go higher than this. So this may be something like, I don't know, like 500 millivolts, something like this. And so in the end, what I want to do on the final design, I want to also include a trimmer, and you can then use the trimmer to kind of get out, or get the maximum cutoff frequency that's possible. So that would be like right below the point where the signal starts to drop out. So here it starts to drop out, so let's go back. You can still hear some weird behavior there. Like I'm turning at the top end of the potentiometer, and you can hear that there's like this strange volume drop in this one pocket of the potentiometer, basically. There. Okay, so we have to lower the threshold even more. See? That sounds great. Okay, so let's try to send in an LFO. Okay. Right, so what I would try now is I've completely closed the potentiometer at the moment. So it's set to 0 volts. So I will try, wait, let me get rid of this. I will try to do the same thing that I did in the simulation. So my goal was, just to reiterate, my goal was that I wanted to minimize the interdependence between the single CV sources. So we have our LFO here, which is one CV source, and also we have our cutoff potentiometer, which is another CV source. This is set to 0 volts at the moment. And with this set to 0 volts at the moment, the response of the filter to this CV sounds like this. And now what I will try is I will try to remove the potentiometer, and ideally we should have the same response, or we should hear the same thing, because the CV is doing the same thing to the cutoff frequency. So let's try this. Whoops. I know why that is. That is because I've connected the cutoff potentiometer not to ground but to the negative rail. So let's try this with a connection to ground. And before you asked, I did that because I wanted to be able to pull the cutoff frequency, or I wanted to be able to set the cutoff knob basically below 0 volts in order to be able to like set a kind of a virtual, like a cutoff frequency below 0 hertz. So to pull down the CV basically. But let me see where the, here's one. Perfect. So we will put this guy in here. And we will put the potentiometer back in. And then put this guy back in. Okay, so the potentiometer is still set to 0 volts. And now what I'm going to do is I'm going to remove this. Let's see what happens. Stays the same. So, mission accomplished, I guess. And on the other side of the spectrum, what we can do now is we can use the cutoff to kind of raise the base frequency, the base cutoff frequency. So you will see that it kind of moves the whole movement of the CV upwards, basically. I don't have better words to describe this. I hope this makes sense. So. Okay, I hope this makes sense to you. I really feel like I'm not explaining this very well, like what I wanted to do. But rest assured, we have accomplished what I wanted to do. So what we can do now is we can do what I promised we would be doing, which is turn this into an LED filter. Okay, so the idea is very, very simple. And this question came up a lot, actually. People were asking, if you are using diodes here, can't you just use LEDs instead? Because LEDs do the same thing as diodes. They block current in one direction and they allow for current to go through them in another direction. They just happen to have the side effect of, like, lighting up when there's a current flowing through them. And I thought about it and I simulated it and I saw, yeah, it should definitely be possible. We just have to make a few minor adjustments to the design. And to figure those out, we will have to go back to the simulator. So let me change to the simulator. Boom. Okay, there we are. And I promise this will be very quick and painless. So the first thing that I did when I tried this out was very obvious. I just said, okay, you know what? Let's just get rid of all of these diodes here. Boom. And let's just replace them with LEDs. And like I said, in theory, this should work just the same. But as you can see, if we reset the simulation now, and maybe I will get rid of this triangle at the CV input, and I will instead just be using the cutoff knob for now. Okay, so as you can see right now, I have set the cutoff to 0 volts. So here at this point, 300, okay. Let's make sure it's really 0 volts. Okay, so now we're nearly at 0 volts. So this means that our filter should be closed, and it is closed, which is great, because it's what we want. And now the question is, what happens if we turn the cutoff knob? And as you can see, I've turned it all the way. We have a very, very positive voltage here, and we have a very negative voltage here. But our LEDs are not lighting up, and we also don't have any signal at the output. And the question is why? Well, it's very simple. I mean, diodes and LEDs are similar in kind of the way they function, like what they do, but they obviously have different characteristics. And we talked already about it in the chat. The thing is, different LEDs behave very differently. And as a rule of thumb, like just from what I saw in the circuits that I tried, and from what I kind of saw my diodes, my LEDs do, is that roughly speaking, one LED behaves like a string of 3 small signal diodes. So one LED, one of these, behaves like 3 of these. So they basically need a much stronger voltage between these two points for them to actually start conducting in any meaningful way. And that's why our, like, how much do we have? We have 800 millivolts up here. We have minus 800 millivolts down here, or 900. So that's in total, that's what, 1.2 volts. That's not enough to activate our 6 diodes here, or 6 LEDs here. So what we have to do is very simple, actually. We have to raise the threshold, or in our case, lower, because remember, like, we turned all of this stuff around, so positive is negative now. But in effect, it's the same thing. So we have to lower the threshold. Let's try. Let's go with. I mean, from what I said, if it's really like as if one LED is 3 small signal diodes, then we should just be able to triple our threshold. So we go from minus 1.2 to minus 3.6, I guess. Let's apply this, and boom, we can already see that there is something happening now, which is great, but it's still very filtered. And this is not ideal because, the cutoff knob is set to full blast at the moment, and the cutoff frequency is still very low, so it's not exactly what we want. So let's look at the voltage here. We are at minus 2.4, which is still probably way below the voltage that we want to have. But to be honest, I'm kind of confused as to why the voltage here is now so much lower than our threshold. That is kind of confusing. But I guess what we can do is we can just lower the threshold more. Let's go to minus 5. This gives us minus 3.4. Maybe I have to drop this resistance here down to get more of a match. Yeah, true. Interesting. Okay, but it doesn't matter so much. Okay, so for this kind of clipping, apparently you have to watch your impedance here. So yeah, what I did just now was drop this resistance down, because I was wondering why we have a lower voltage here at this point than we have down here. And we still have this. We have minus 5 down here. We have minus 4.7 up here. I guess it's probably due to the current that we're pulling in here, and probably the interaction between this impedance here and then these impedances here. But we'll not get into that. So for now, what we will do, like on my breadboard, I have a 10K here. So I will keep it at 10K, and we will just decrease the voltage here further. So just lower the threshold, and then we will see if we can get decent results. Okay, so as you can see, we now have basically unfiltered output. Well, not unfiltered, but a very high cutoff frequency. So the output looks very square, which is great, which is what we want. But for my taste, and I mean, this is just the simulation, but for my taste, these diodes look a bit dim. So you can see that they are like slightly lighting up, you know, they're slightly not black, they're slightly going red. But for me, this is not good enough. Like I really want them to light up when the filter is fully open. So the question is, what can we do about that? Well, of course, we can try to just drop the threshold down. Let's just go all the way. Let's just go to -12. And then you can actually see in the simulation that even the simulation is glitching out if we're going down to -12 volts. You know, you can see that it's jumped up, like the center of the upper waveform jumped up to, I don't know, something like 11 volts, which we probably will also see on the breadboard. But our LEDs are lighting up. But we don't want this glitch. So what can we do? Well, I mean, the first thing that we obviously have to do is we have to drop the voltage here down. So let's go down to, let's say, -7 volts. And it still seems to be, oh no, it's not glitching out. Okay. So at -7 volts, we get a probably decent output. I mean, you can still see there's some glitching here. I have turned the resonance completely down, so it's not resonance. You can see that the simulation is already telling us, hey, there is something funky going on. So what I decided to do, like instead of pushing the diodes like so much, or rather the op amps so much, what I decided to do is I decided to increase the value of these capacitors. Because if we bump these up, to 4.7 nanofarad, then you can see, no, we need to wait until the glitch is gone. Move. Okay. Then we can see there's still some weird stuff going on at the edge. But yeah, I was hoping by increasing the capacitance here that we could, you know, push that glitch thing a bit back. But I guess okay, let's do it just for simplicity's sake. What we're going to do is we are just going to go back to the 1 nanofarad, and we are just going to try it. Like maybe it does work with such a low threshold. But okay, so this is what we're going to do. I'm going to go back to the breadboard, and I'm going to exchange all the diodes in this string with LEDs. And then what I'm going to do is I'm going to drop the threshold voltage way down. And then we will see what happens. So let me switch the camera view, and now I can look at the comments again. Can you put an LED strip to make a huge ladder VCF? Or are they not in series? LED strip? I'm not sure what you mean. Usually they have sets of series in parallel. Maybe explain to me, like I want to be in on the thing, what an LED strip is. But yeah, for now, let's get to it. Oh, one question. Do you guys have any preference on LED color? So I have an assortment of colors here. So I have white ones, like these are like kind of milky, you know, diffuse. I like these. I also have like the classic red ones. And then I have a bunch here. I have another thing somewhere in my desk. Let me look. No, these are potentiometers. I have this really stupidly designed desk. It doesn't have a drawer. It's just you know, hollow in the middle, and it looks nice, but it's so impractical because anything you put in there, it's a complete nightmare to find something. So here, these actually I've bought this set to when I was doing my in-person workshops, because I was working mostly with people who are very, very new to electronics, and you could really like I always like when I packed the kits for everyone, I always made sure to pack like 3 times the amount of diodes that they need, and I would still always need to bring this pack of extra diodes because there were so many dead diodes in these workshops. It was incredible. Okay, so let's see how you voted. Blue, yellow, white, red, not white, red, green, red, blue make me go crazy, orange, yellow, or red, green, I like orange. I guess you have to try them all anyway, and of course mix some colors. True, because that's a good point. Different colors of diodes actually have different characteristics. So I think that how was it? I think that red diodes actually use up less current to light up. Is that right? Not sure. But yeah, of course, they're always all going to have different characteristics. So the question is, which one are we going to start with? And I don't see any overwhelming support for any color. But I read red a few times or orange, red. Blue ones, they're good for retina. If we increase number of stages, will we need to increase voltage difference between ends of ladder? Yes, of course, definitely. You have to increase. You will have to increase the voltage difference. That's something that you have to fine tune, definitely. Orange, blue, green, red, orange. Burning LEDs is fun. You can see the plastic cooking and bubbling on the inside. True. Blue LEDs won the Nobel Prize. Blue has high voltage drop. You should go blue. Red has a lower forward voltage. Orange, yet red, yellow, blue, pink, orange, orange, orange. Okay, so I would say that we might start with red ones just because they're a classic, and you can't really go wrong with a classic. So I would say we do that. One thing, someone on the Discord warned me earlier that LEDs have a way lower like reverse breakdown voltage than regular LEDs, regular diodes. So I'm wondering if I maybe I do this later, but I should maybe put in a diode here after this CV to make sure that we never reverse bias our LED string. I guess if we're just using the cutoff knob for now, it's fine because it goes to ground, so it will never. Just using the cutoff knob, we can never like reverse bias the string. But so let's add this in later. Okay, so like I said, I think I'm going to start with the red ones. The only thing that might be a bit hard is you can see that this diode is very stretched. Like it's stretched from the last capacitor back to the op amp here. So I will have to see if I can fit my diode in here. Also, another thing that is really annoying, I think, about working with diodes is, I don't know what your experience is, but I feel like they're often like they are way more often broken coming out of the box than any other component. So oftentimes, I would pick up an LED, put it in my circuit, it doesn't work, and I think that I did something wrong and the circuit is wrong, but the LED is actually broken, which is annoying. So maybe prepare for this not working because one of the LEDs is busted. So let's see. Boom. And then this one. Okay, so like I said, we go with red first. And then the next... Actually, I meant to say this. I don't have any orange LEDs, so I actually can't accommodate you there, even though Team Orange was very prominent. Please try gumdrops with some cut leads in place of the LEDs. Gumdrops? Huh. You will have to, maybe it's a joke and I don't get it, or you have to explain it. Okay, so now I have to think. The long leg goes to the top of the ladder. I shouldn't have pulled them out so hastily. So which one is which? Wait, this one is the top because I still have the 2K resistor here. Boom, that goes in. And then we just jump, whoops. And then we basically just jump from capacitor to capacitor with LEDs. Okay. I really wonder if this sounds good, because it would be nice, you know, if you build a module, and then maybe you use the smaller ones. Like I have these very small red LEDs. I think it would be nice to kind of incorporate them into the panel, because I mean, it's always nice to have LEDs on your panel, but I think for me it has like a kind of different feeling if they're actually like an integral part of the circuit. You know, if you know that the LEDs are kind of actually filtering the sound, that would be cool. Stick cut of component leads into the bottom of some gumdrop candy so that they look like LEDs. Okay, and then you want to know if that works. I guess it won't. Maybe I'm too dense for the joke. So. Okay, almost done. 2 more to go. ElectroDock is a great app for pinout and electronic calculators. They have all the LED specs. Good tip. I always find myself just running to Google and then, you know, just typing in pinout and the chip that I'm looking for. But it can actually be kind of annoying sometimes. You know, sometimes there's like these pages that say they have a data sheet, and then you go there and they don't have it, or it's completely wrong, or it's super annoying. I was also thinking about like buying one of these component testers. Like there's these dedicated things that just have like slots for different kinds of components, and they can measure all kinds of stuff. You know, like capacitance and also resistance, of course. I guess also stuff about diodes. I'm not sure. Maybe that would be a good investment. Okay, now the moment of truth. The question is, can I get this diode to fit, to kind of bridge the gap from here to here? This might actually be difficult. I'm not very optimistic. Let's see if this fits like this. Nope, it has to go 1 row further. Okay, so I will see if these other diodes have longer legs, maybe. Yeah. But I think they look basically identical. Okay, so what we will have to do is we will have to go with one of the smaller ones, which is not that great because they probably have a different forward voltage drop and everything. Oh. Or maybe we could just go with the small ones for all of them. I think that's probably a better idea. There's another one. We need 6. So 1, 2, 3, 4, 5, 6. Perfect. Okay, sorry guys. I have to rip these out. And we will go with the small ones, which, to be honest, I think they might even look a bit more stylish. Okay, number 1. Number 2. Yeah, there are very very cheap things, definitely. I was thinking about maybe, like I saw in my local electronics store, I saw this one multimeter which also had like the capacity to test components, and it also had a built-in oscilloscope, but it was like something like 300 euros. And I saw this, and, it was just like, I want this. But then again, I mean, it's 300 euros, and the question is it really that useful? I haven't decided yet. Maybe, I mean, for the stream, it would actually be nice to have just a small oscilloscope on hand that I can just put in frame. So that might be a way for me to justify the purchase. So let's see. Okay, nearly there. And the final one. Wait, now I have to go long leg here, and I have to go short leg on the last one. Okay, now the only thing is we should make sure that we don't destroy these because these are the only ones of these type that I have. And if we destroy these, then I will have to shuffle everything around on the breadboard, just to make this work. So would be nice if we don't destroy this. If you buy combined stuff, keep in mind if one function is gone, it is useless at all. If I go for dedicated DSO, a dedicated multimeter, and a spare multimeter, that's a good tip, I think. Yeah, true. What do I dislike to use? The wires with the black DuPont connectors on the ends. Not quite sure which these are. But yeah, okay, moment of truth. Let's see if we can get this to work. So I'm still sending in my oscillation. Our threshold is still set to the old value, so it's actually reasonably low. So I don't think we run into any issues there with the current being too high for the diodes. But I really doubt. I mean, we have a 2K resistor at the top op amp, so I really doubt that we could have too much current going through these diodes. So I think we should be quite safe. So I will turn this on now. Whoops, I have to connect this, of course. Boom. And now let's see. Okay, nothing. And I will try to turn up the cutoff. And we get nothing. Predictably, I mean, like I said, I think this the voltage between the top and bottom op amp, it's just not big enough to actually activate the diodes in any way. So what I will try is I will change the threshold, and then we'll see if that does anything. So let me turn up the cutoff knob completely, and now I will mess with the threshold voltage. Problem is that I'm kind of going in blind because I don't know which direction is the right one. Let's try this first. We get nothing. Nope. Then let's go the other direction. Let's see. Come on. Come on, come on. Okay, know what? We'll get out the multimeter and we will see what the threshold voltage is set to right now. If I can find it. There it is. Okay. So, because I have the gut feeling that maybe one of the diodes is broken, or I messed up the orientation of one of them. So that's two things that we will need to check for, but only after I know that my threshold is set correctly. So I am gunning for something around like -6 volts maybe for the threshold. And since I'm going blind about the way I turn, let's just test this. So one lead goes to ground and the other one goes to our threshold right here. Whoops. And I don't know if you can see, but we are at -4.2 volts now. So let's go more in this direction. Sorry, this doesn't work. Okay, so you have to go blind for a second there. I'll turn this. And now we're at -5. And now we are at -6 volts. Let's go up to -7 maybe. Okay. So our diodes are still not saying anything, but as you can see, we are already at -7 volts for the threshold. So this is probably not the problem. Let's see what the voltage is that we sent into the diodes. So that should be here, should be our CV. Okay, so you can see we are sending in -2.37 volts. So I'll just quickly check the simulation. What we sent out there for them to light up was actually -4. So my suspicion is, let me turn this off for a second. My suspicion is that the feedback resistor in my CV op amp is probably not a 20K. It might actually be a 10K, and that could explain why we're not able to push the voltage here up enough to get these diodes to light up. So let me check. Let me check on this resistor here. So this should be it. Okay, and we have a 10K. Okay, so first step, what I will do is I will replace this guy with a 20K. Or 22K, it's also fine, I guess. Such a small change to the circuit, but still so much room for stupidity and bugs. Okay, so with the 22K, I will turn down the cutoff knob for now, so that we don't burn our diodes in the worst case, and let's see. Okay, let me turn this up. I think I heard something there. Do you hear that? Ah, it's just noise. It's just noise. Okay, so my next suspicion was that maybe I have set up the diodes wrong. So let's check on that. This one looks okay. This one is also correct. Yes. Ah, that one was wrong way. You see? Short leg here, long leg there. It should be like this. Okay, and the final one, this one was correct. Okay, and then this guy, I guess, is also correct. Yeah, No, it was wrong. It was actually also wrong. Amazing. Okay, it should be like this, because positive here, negative there. Current goes from here to there, so it should be like this. Oh man. Guess I was getting too excited. Okay. Yeah, now we have to pray that none of these are broken. That's another thing that might go wrong. Okay. I turned the cutoff way down. Everything is plugged in, and let's see. Oh, one more thing. I haven't turned on my synthesizer. So even if this did work, we wouldn't hear anything. So now it's on. Okay. Ha! There it is. Okay, so we can clearly see, or you can hear, that the threshold is still too high, because right now the cutoff knob is turned all the way to the right, and the filter is barely open. Right? So now the question is the problem the threshold, or is the problem the gain of the op amp? So what I will first try is to mess with the threshold and see if that does anything. Nope. Or maybe slightly. Well, let's just find out by measuring, right? I mean, obviously the diodes are not lighting up yet, but the fact that they are filtering makes me optimistic that it should probably work out in the end. Let me turn this down. Sorry. So I will first measure the threshold, and then I will look at the voltage that we are, the processed CV that we are feeding into the diodes. Okay, so you couldn't see this, but I have already pushed the threshold to -12, so this is not okay, so I should really bring this down again. So I would say for now we are going to go down to, let's stay at something like -7. I think in the simulation that was that looked the safest. Okay, so as you can see, -7. Oh no, and then I also wanted to measure the voltage that we are feeding the diodes. So as you can see, we are at -4.4, so we are still nowhere near the threshold. So what do? It's very simple. We increase the value of this resistance again. So right now we're at 22K, and I will go up to, well, if we want to double it, I will go up to 47K. Bring in your oscilloscope for proper measurement. If you could see my desk right now, you would understand why that's a problematic proposition, because it's completely crammed with stuff. And just getting it up here is a challenge. We can do that maybe in the end to kind of, look at what the filter actually, how it performs. But for now, I'm just focused on making the diodes light up. Okay. Moritz, question. Who is best, Kraftwerk or FX Twin? I wouldn't want to say, I wouldn't want to judge who is best on a universal level. And I couldn't, of course. Just for my taste, I listen to FX Twin more than Kraftwerk. So maybe that answers your question. Okay, let's see. Get a bigger desk, but you talked about moving for space already. Yeah, the problem is in this room I couldn't cram a bigger desk. That's actually a problem. So I have to move to be able to do that. Kraftwerk is more influencing, right? I mean, sure, like they're pioneers. I mean, they did a lot of stuff that a lot of people copied afterwards, and I guess the kind of music landscape would look different without them. But I don't know. I mean, I had a phase where I was more like into 70s, 80s stuff, but recently I kind of strayed away from that. So yeah, now I'm more like into the 90s techno stuff. So I really like Basic Channel right now, for example. I don't know if you guys know them. Super cool stuff. Like when I first heard this, I couldn't believe that they did this like in like 92, 93. Like super modern, super minimalist, kind of moody, like melodic. I think like dub techno is like the official name. Really like this stuff. Then FX Twin, of course. Today I discovered someone. What was his name? Let me look it up. Also, I think the album that I listened to was from like '96. Where is it? Come on, where are you in my list here? Shit, this is very anticlimactic. Ah, no, there is Porterix. Biokinetics is the album. Like super cool, like super experimental, like kind of out there, especially for '96. So recommend it definitely. Okay, but let's find out. Let's find out if this works. So I've already plugged in the power supply. I've plugged in my oscillator. Let's turn this up. Ha! I don't know if you can see this, but the LEDs are actually lighting up. Okay, let me turn up the resonance to kind of judge where we are at with the cutoff frequency. Interesting. That sounds completely different, the resonance. That sounds really different. It sounds more bubbly. Do you know what I mean? Maybe if I turn this up. Yeah, I would also say it sounds kind of MS-20 style. There's one thing that I noticed. I think it's actually glitching out at the top end again. Let me see. You hear that? Like when I turn the resonance way up, you can hear it. There's like this area where the volume drops. So I guess we will have to adjust the threshold again. Let me see. Right, and now we have the problem that I was talking about earlier. So if I completely turn this up, then our diodes do light up, but they are not very bright. You see? And that is because I just dropped the threshold. Because I dropped the threshold, but dropping the threshold also means that we drop the intensity of the light. So I can show this again. If I raise it, then the lights go brighter, but then the filter starts glitching out again. You hear? Okay, so one thing that I would like to try, I'm not sure if this is going to work, but I would like to try, and this is a quick one, I would like to try and exchange all these 1 nanofarad caps with 4.5 nanofarad. So what I'm hoping to achieve with that is I think I could achieve, how do I explain this best, to kind of align the this is bad, the capacitance with the effective resistance of the diodes. I don't know if that makes sense. But right now you can see, if I turn this up, for most of the cutoff frequency spectrum, the diodes are off. They don't light up. They only light up at the very top end. You see? Only there. And that's because the capacitors, you know, they fill up very quickly, and that's why even if the diodes just light up very slightly, so if just a very small current is passing through them, the capacitors fill up so quickly that we are already like at a very high cutoff frequency. So what I want to try is I want to use bigger capacitors so that we can kind of shift this down, so that the cutoff frequency kind of aligns better with the lighting up of the diodes. This is not very well explained, but let me try it and we will see if it actually works. Okay, question time. Where can we find this type of capacitors? I suppose they are film capacitors. You mean these? They are, I always promote the brand, I'm not affiliated with them. They are WIMA caps, so WIMA. If you Google them, you can find them en masse. Like I think they also operate worldwide, and I can really recommend them. They're great. Okay, what else? Isn't it all that the problem? I mean, don't you need the LEDs below the voltage drop for them to work as voltage controlled resistance? I don't know what you mean. Okay, let me just try to exchange the capacitors. Luckily, I have 4 and 7 caps that have the exact same form factor and footprint as the 1 nanofarad, so we don't need to shuffle anything around. It's very easy. Okay. Let's see, we need 5. 1, 2, 3, 4, 5. Perfect. Now I have to get this right. This one goes in here. And boom. Okay. Yeah, let's see. I think they do light up just a slight bit like earlier. Oops. I will turn down the threshold here so that we don't have the glitching problem again. And let's go with that. Sounds okay to me, I guess. So yeah, I would say they are a bit brighter at the top end. I think they go like they start glowing a bit earlier. for my taste, this is still a bit too late, I would say. And also I'm noticing that the bottom end of the cutoff knob is basically dead. Like it's dead till something like 12 o'clock. Okay, let's check the comments for a second. I think the LEDs are only going to light up when the filter's fully open. I'm not sure. Like I think. You know what? Let me try this with. I think I have 10 nanos flying around somewhere with the same footprint. So we can try that, and then we can basically put a rest to this. Ah, no, missed. My 10 nanofarad are actually huge. These won't work. And these, wait, let me look at these. These are 22. No, they're too wide. You can try to use super bright LEDs. They usually have clear enclosures and have a decent brightness with low current. Those generic red LEDs usually require about 20 milliamps to get decent brightness. I might be wrong. I mean that in your original design you needed the voltage across LEDs to be below 600 millivolts, so they would be in their weird exponential region. I think they're actually always exponential. Like that's not the problem. I think the problem is just what other people have pointed out, that once the current gets so big that they actually like really go bright, then it will start to glitch, like necessarily. And I think that there might be something to it. So I guess you might be right. And also we can see here, like I said, that now most of the range of the potentiometer is dead. Because the caps are so big, so this is probably not a good not a good workaround. Okay, so one thing that I want to try is wait. So I think I will go back to the one nanofarad capacitors. Simply because I want the CV range to be more spread out. You know, to so that the bottom end of the cutoff knob is actually usable. And then we lose a little brightness, but maybe that's not so bad. Maybe like a faint glow is also a nice effect. Let's see. Okay. Okay, so I have to lower the threshold because it's glitching out again. Let's see. Can you even see the glow? Okay, so one thing that I would also like to try is, as you may remember, like I haven't explained this all that well because, to be honest, I still haven't completely figured out like how it works. But as you might remember, is that I have put these two diodes in the feedback path in order to kind of prevent the resonance from going overboard. You know, from escalating so much that the output just disappears. Because that is what happens. It just starts to oscillate to something like 50 megahertz, 40 megahertz, something like that. It's just super quick, super loud, and then it's just gone. Yeah, the synth is so much louder because the output signal is, I think, 5 volts peak to peak. So let me, and I have my interface actually completely turned down. So the only thing that I could do would be mess with these resistors, but right now I don't want to do this, because instead what I want to try to do is, like I said, the diodes here are used to kind of counteract the exponential escalation with the diodes here. This is a bad explanation, but that's what they do. And right now I'm thinking maybe the weird resonance that we're hearing, like this weird, oh no, it's gone. Why is it gone? Interesting. Did I pull out the cable? What happens? Okay, so what I'm thinking is maybe try to exchange these diodes with LEDs, or with the same LEDs if I have them still, and see how that affects the sound. Because I think that the characteristic of these diodes in the feedback path kind of, you know, they kind of interact with the characteristic of the diodes here, and that's kind of giving the resonance like its character. So let's see if I can dig up 2 more of these small red ones. I think I can. And then let's see how that changes the resonance. So just to keep it in memory. Okay, just keep this in mind. I will now exchange the diodes for these guys. Interesting, there's some noise creeping in. Ugh. You should never do this. Like, I really hate myself, but because I didn't have so much time to prepare the layout, I had to kind of double book some of the breadboard's tie points. And it's just a bad thing to do. Okay, all set. Let's see. It doesn't sound very healthy. Okay, so if I turn up the resonance too much, I mean, here it basically sounds just like before, I would say. But if I turn it up too much, what the hell? Yeah, that's really weird. Whoops, I'm very sorry for wrecking your ears, and I'm very unsure what happens there. Ah, okay, so you said you want to hear it without clipping diodes in the feedback path. We can try that. Let's try that. Let's try that. I will take these out. And we will check it out. Okay, so here's without resonance. And you can actually hear, I think. Oh no, it's always just when I'm touching this, I think. Okay, so now the resonance is completely turned down, so I will just turn it up a slight bit. A bit more. And then you can see. So, I don't know, basically what I've deducted is that if you don't have the clipping diodes in the feedback path, then the resonance just you know, I feel like at lower levels, at lower feedback levels, it's not enough of a positive feedback loop to kind of completely escalate. But as soon as you go past a certain point, it's just gone forever, and you just have like such a strong positive feedback that you have this ultra quick oscillation that just, you know, kills the output completely. So let's check it out again. Boom, there it is. And the sad thing about it is that you don't even get, like, it's just sudden. Like, you don't get any build up to when it then actually happens. So it's just boom and it's gone. But I'm still wondering why these diodes like give this super like cyberpunk sound. Let's just try another type of diode. Maybe that will change things. So I will use these bigger red diodes in the feedback path now. I can never remember like which way I put them in. Okay. Boom. Let's try this. Let's turn the resonance down for now. Okay. And now I will turn up the resonance. Same thing. Okay, I have a suspicion, actually. I have a suspicion. The feedback path right now, how I've set it up is I have a 100k resistor here. I have a 27k resistor to ground here. And the 100k resistor is basically in parallel with the LEDs. And so I think what happens basically is that like with a small signal LED, so with a 1N4148, I don't know how to explain this properly. The balancing between the 100k resistor and the diodes is just right. So whenever the positive feedback loop kind of escalates, then the diodes just step in and they basically just push it down again. You know, they just keep it from going crazy. And the problem is that these LEDs, of course, they don't act like those diodes, so they need a stronger voltage to kind of activate. So my guess is that they don't activate at the right time. They only kind of get active when it's already nearly too late. So when the feedback loop is already so in motion that our filter is glitching out, and then they kind of, you know, then they get active. They kind of drop. They kind of reduce the amount of feedback, and then it just goes up again, and you have this ultra fast oscillation, which is just like this strange digital noise that we are hearing. I think that's the reason. I think someone said it in the chat. Oh yeah, I think that happens because LEDs have a much higher voltage drop than, yes, that's exactly what I said. Okay, so what I will try is I will just try to drop these resistances down. So right now I'm at 100k and 2k7. Or no, should I drop them down? Let me think. Yes, I should. I think I should drop them down. Should I pull them up? Help me, guys. I will just try to do 10k 2k7, and if that doesn't work, then maybe we go up the ladder. So we go to like 200k, and then another value here. So let's try. Let's try 10k. LED is very slow. Yeah, might also be a problem. Okay, and then we need a 2K7 here. Yep. Problem is with a 2K7, like normally I have these nice 0.4 watt resistors, like these small ones, but for like these freakish values, I only have like weird. Like when I was starting out, I bought this big pack of resistors, and they were just in all shapes and sizes. And these have, I think you can't see this, but these have such thick legs. You can't. I mean, you can, but it's very hard to get them into the breadboard. So I do not recommend. And it's a nightmare to bend them. Like they don't want to bend. It's super annoying. Okay. So let's see if that does anything. Is it still working? I haven't plugged it in, yeah. Sounds good to me. Let's turn this up. Okay, so it's better, I would say, but I think I have to exchange these big ones with the small ones again. Because probably like these have different characteristics than these ones, and we should probably match those to not go absolutely crazy on the resonance. Some of this has sounded like magic smoke. Yeah, definitely. I'm actually surprised that nothing broke yet. But yeah, if this works, I mean, even if this doesn't work, I will go back to the standard diodes, and then I will turn off the lights, I guess, or turn them down, and I will play a sequence, and we will hopefully be able to admire these LEDs. Boom. Okay. Let's see. They still work. Let's turn this up. No. Okay, there's still this point where they just completely. Yeah, maybe it is doable, but I guess not tonight. So let's drop these guys again. Now we'll go back to the 27K, 100K combination here. I hope I still have the resistors laying around. Yeah, this is the messiest you have seen my desk, definitely. And interestingly, I feel like this is like the simplest thing that I've done on a live stream. So all the other streams I feel like have been more complicated. And yet here I am. Yeah, I don't know. So put the LEDs back in. Sorry, the diodes. But honestly, I wouldn't have thought that using the diodes instead of the using the LEDs instead of the diodes would change the sound of the resonance so much. It's interesting. Every time I stand up out of my chair, I get a little static shock if I touch something metal, but even never got magic smoke or broke a component. Yeah, did you ever get a shock when you touch one of your components? Because I never had that, so. But I also don't wear like electrostatic discharge gloves, so. Okay, so what I will do now is I will make you feel a bit more at ease, because I will clean this up a slight bit. And then I will, well, first of all, let's start simple. So first of all, I will use an LFO to kind of make these light up and look pretty. One thing that I will add, just as a precaution, like I said, I will put in a diode here to make sure that we don't reverse bias our diodes, and because we don't want to wreck them. Okay, hopefully this works. Let's see. Okay, but now we have to adjust the threshold, because as we all know, it has a diode drop. So the voltage on this side will now be 600 millivolts, approximately 600 millivolts lower than what we had before. So I have to adjust the threshold. Okay. Cool. Now let's try it with an LFO first. I will dim the lights. Okay, maybe dim them even a bit more. Okay, let's see how this looks. Well, I guess this will look nicer when I'm using a sequence. So let me bust out my sequencer. I have to turn up the light again, I'm very sorry, otherwise I can't see. Okay, give me a second. It's really horrible. I always run out of power outlets. Like no matter how many multiples I put in here, it's just never enough, I guess. So I will reveal more of my horribly messy desk just to be able to show you the sequencer. I feel like it might be nice to see it. So okay, I'm afraid to break something though. I'll turn this off for the second. We actually don't need the multimeter anymore, which is nice. Push this up. And I will get rid of this mess. Okay. No, it's not Baby 8. It's boring. It's just my beat step. I'm just realizing there might be a problem because I mean, of course, this is also very bright, and so it might kind of overpower our nice filter. But let's see. So I need to send in my envelope. Boom. That should actually be it. Okay. Let's see if this works. Of course, I have to go into the sequencer. And of course, it doesn't work. Oh no, it does work. I unplugged it. This is also something that I would like to just have down the line, you know, like a proper desk for live streaming. I mean, this is very, very much in the future, but it would be great to have just all of this set up already, and I don't have to worry about, you know, managing all this. That would be my dream, I guess. Okay, let's see. Sounds super weird. I have a suspicion. Maybe now we really have this, or we kind of attenuated this problem with the, you know, I feel like that I will turn down the speed of the sequencer, and I will turn on the lights, of course. So, boom. Yeah, I think you can hear that, you know, whenever the CV goes so low that the filter basically closes, then when it opens again, you get this weird sound. So right now I've turned the cutoff knob beyond like a certain point, and then it sounds like normal-ish. But then when I turn the cutoff down, you can hear it again, I guess. So yeah, I think I heard some when I was researching stuff for my filter, like with the small signal diodes. I think I kind of read somewhere that there might be an issue, like if they're not matched properly or if they're not close enough, then you get these kind of like CV bleed problems. And that's what you hear, I think. It's like whenever the filter goes closed and then goes open again, then you kind of hear like the transients, I think. We can try this by increasing the attack. Yeah, I think that is the problem. So yeah, Michael, like you said, Usynth, I read his post. Like he commented on some posts that you have to match them to prevent CV bleed. And maybe for these small signal diodes, it's not that necessary because they are kind of close together anyway. But I feel like with these diodes, I mean, I feel like you can see that this diode is dimmer than the others. I think there's differences between all of them, but I might suspect that that they're not very close together. I think they're much further apart than regular diodes, and that might lead to the horrible sound that you're hearing here. So I think while this does work in theory, I think you would really need to match these to get a proper filter here. So mission not really accomplished, I would say. I mean, partly accomplished. They light up and the filter works like in theory, but yeah. It's easy to match the LEDs. Is that sarcasm? I'm not sure if it's easy. You could try it, I guess. Damn it, I couldn't make it on time, but looks cool what you did there. It looks cool, but I can show you again, it doesn't sound so cool. What I'm going to try, I don't think this does anything. I was thinking about maybe removing this diode, but I don't think it helps. So yeah, what's the moral of the story? Well, no, it's easy. A multimeter on diode settings should get you the forward voltage. True. But in this situation, the problem is that I only have 8 of these. And so I don't think it's enough to get matched ones. Let me check. Just to verify that they are like somewhat far apart. That's what I would like to know. So, oops. I always cringe thinking about plugging my BeatStep into anything I build. Yeah, in the beginning I was also very very hesitant to do this, but I feel like now it's more probable that my circuit dies than that anything else dies. So okay, so I hope you can see this. You can see that this diode has forward voltage of 1.75. 1.75. So let me try to breathe on it and see if it changes anything. Interesting. For the small signal diodes, breathing on them like changed this rapidly, but it seems like with LEDs it's not that big of a problem. Okay, let's try another one. So let's remember 1.75. So I'll try this one. This one sits at 1.77. I mean, it's 20 millivolts. 21 millivolts. Interesting. Let's try another one. This one is 1.75, like the other one. And let's try another just for fun. Maybe I have 8. If I have enough that are in the same ballpark, like around 1.75, then we could try that and see if it changes anything. Oh, this one's also 1.75, so it looks good. I didn't sort them. Shit. Okay, let's try this one. Boom. This one is, yeah, I would say it's the same ballpark, so 1.75. Goes in this pile. And then this one here. And then this one here. 1.75 again. So I guess this one here was the black sheep. Yeah, that one is the 1.76. So this one goes in the shit pile. Bye-bye. Let's pray that we can find 6 that have the same forward voltage drop. Yes, 1.75. And then this guy here. Okay, this one's 1.76. So we also throw this one out for now. And where are the other two? Maybe in here? Yeah, there's one. There is one here. But the question is where... I had 2 more, I'm very sure. It would be quite a surprise, an amazing surprise, to have your VCF respond to light. Yeah, light dependent VCF. 1.744. I would say it's a candidate. It's not perfect, but I remember like when I was matching the small signal diodes, like the 1N 40, 41, 48, I think they at maximum they were like 4 to 5 millivolts apart, and those were like the most extreme ones. So my theory has kind of been validated. Okay, this one's perfect. This one is perfect, and now we need just one more. Put this guy in there. Let's see. Oh, this one is broken. Or is it? No, that was just the wrong orientation. Boom. Yes. I don't know if you can actually see this, but this is again 1.75. So I will now try to use only the LEDs from this pile, which have like a decently similar forward voltage drop. And maybe we can end this on a high note with this stuff working. So let's see. No. Okay. I just built an 808 snare drum and bass drum on the breadboard or on a PCB or strip board. Do you guys generally like the 808 kick more or the 909 kick? That would be interesting to me. $909 both. Yeah, for me it's also the 909 actually. I feel like the yeah, true. I mean the 808 kind of has its place. I think I like it more to pitch it, you know, to do bassline stuff like that. But just for like really like percussive and like techno stuff, I definitely prefer the 909 actually. And what about the 606? Where can we find the schematics for the 808 DIY version? Oh, there's so many. I think you can actually find the original schematics. You know, from Roland, from the user's manual. Okay, let's see. Oh yeah, I need to plug this in. But at least it lights up, so. Interesting. So my VCO is so slow that it's basically in LFO territory. And we get these nice, let's increase the resonance. Interesting. Okay, but that's not what we're doing. Let me turn this guy on again. Boom. Okay, we'll turn this guy down, and we will see what the sequence sounds. I would say it's better. But I would say it's definitely better, but you can still kind of hear that. I think multiple things. Like one, I think you can hear this kind of CV bleed through, like at the bottom end when the attack hits. I just turned I just made the attack a bit slower, but I think you could still hear this kind of clicking noise. And then also I feel like it seems to me that the CV response is not exponential like with the other diodes. Maybe that's, I don't know. Does anyone know if the relation between voltage for a diode and the current going through it, is it exponential, or is the curve kind of skewed? Because I feel like that's kind of what we're hearing. I can play it again. I don't know. That doesn't feel right to me. But one thing that I will try is I will try to, like this is I think a 47K, if I remember correctly, at the CV input. I think I will raise this up to 100K to, you know, drop the CV intensity down just a slight bit. Maybe this kind of changes our or fixes our problem, or at least, you know, makes it less prominent, but let's see. Can you try out how it responds to light? As I've written above, LEDs can produce current, which might have some effects in this case. Yes, I can take my LED panel and I can blast this with it. But first, I want to kind of see if we can improve the CV response. Great, no, I broke it. Put this guy in here and put that guy in there. And now nothing happens. Let's see if we hear something at least. Okay, that's a bit better. Maybe I'm hallucinating, but I feel like when I turn up the lights, that the cutoff point rises a bit, no? Let's see what you said. The main problem is that LEDs are not very stable in this region of operation due to sensitivity based on light. Probably, yeah. Probably like the response is just not reliable. Probably the easiest way you could put this. But it still sounds somehow nice, unique, and a bit trashy. Actually, to be honest, I think this sounds a bit like the Vectral filter that I built. You know, for some strange reason, maybe there's like some, probably not, but it sounds a bit like that to me. Yeah, let's add a bit of reverb. If I can, maybe. Yeah, I don't know if my cable is long enough. Yeah, this might work. Let's see. Okay, I will now try to turn up the light and see if it in any way changes the sound. I think it actually raises the cutoff point, no? I think it does. Okay, I'll make it slower. Interesting. Yeah, I would try my phone's light, but my phone is what you're seeing this stream through, so I can't turn it on, I feel. Okay, sorry for the abrupt ending there. Yeah, so I would say this is not a completely failed experiment. I would say this is probably salvageable, and it would probably be cool if I could get this to work. But on the other hand, I'm thinking probably to get this to work properly, you would actually need to get some really well matched LEDs. And I'm not sure if it's a good prospect, you know, if I just thinking of like, you know, if I sell kits for this and I have to match all the diodes like so religiously to get them, you know, to work properly. I mean, it's a cool thing. Like I will definitely put this schematic in the description as always, so you can find it there and you can build it for yourself. Try it around, maybe with different colors and everything. But I can definitely see why it's not a more popular choice to make a diode ladder filter with LEDs. Okay, so I would say I will cut it off there. If you have some questions, we can still chill and talk a bit. If you do, please post them in the chat, and I will try to answer them. And I will look at what you've written before. Those two filter module winners, I want the version with LEDs, please. Yeah, I hope with my closing speech there I convinced them that they don't need that, but yeah. What about laser diodes? I mean, probably you could try this with all kinds of diodes. You could try germanium, like some people suggested. You could also try Schottky, I guess. Probably you can find something that sounds nicer than a 1N4148, or maybe you can find something. So I guess you will just have to build it yourself and try around. I think we just established that it is doable with other types of diodes. Maybe LEDs are not the best choice. So simply make your inputs compatible with the open collector outputs of the beat step and your golden. Your inputs, you mean the inputs of this circuit? Or do you mean my envelope? Are there any weird wave shaping you can do in the resonance path to get weird effects? I was thinking maybe wave folder or something. I'm pretty sure you can do that. I'm pretty sure that there's plenty of stuff you can do in the resonance path to give it a different flavoring. Wave shaping might be nice. What else could you do? Filtering even? Not sure. I mean, just pop in a high pass filter or low pass filter, just a passive one. Maybe, I don't know if that works. What else could you do? You could clip it. I mean, but we're already doing this, obviously. Can't really think of other things now, but I guess you can. Wave shaping might be a good idea. Yeah, true. You could put the LEDs just to the CV inputs. You mean just here? Sure. I mean, true. That's something that you can do just for the aesthetics in the final module. But like I said earlier, just what I wanted, like what I would have liked to see is to have diodes that actually have some function in the circuit besides being LEDs and besides lighting up and showing that something's happening. So that's why I was hoping that this would just work out. Problem is, didn't so much. So yeah. Okay, Buck says, yes, of your circuits there, it's a snapping between open inputs and a voltage level, and it's making a poppy noise at each note beginning. You might be right. Actually, my envelope that I'm using is from René Schmetz. It says, I think it's, I don't know what it's based on. And I was always just assuming that the problem is that it's too fast, that the envelope is just so fast that you get the clicking noise, but maybe you're right. I would have to look into it. And if so, it's definitely a good tip. Maybe also change the phase by frequency can shape the sound. You mean for the resonance, right? Yeah, I mean, sure. Like you could try to phase shift it and see what happens. I'll say probably the series polarity protection diode on the CV. You mean that this causes the snapping? It could be. I did not want to take this up because I did not want to burn these LEDs. Maybe that would help it. I'm not sure. But that might be something for another stream. And yeah, I mean, it's almost 11 here. So I will have to end this now. So thanks guys very much for watching. I hope I answered your questions. If you have any more questions, you can always either comment on YouTube. You can follow me on Instagram. You can find my Instagram on my YouTube channel. You can always send me a message there. I will always try to answer. Of course, also everyone who writes in Patreon or on the Discord server gets an answer as fast as possible. Then also, I think I did mention this in this stream, the files for my PCB layouts are now up on Patreon. You can find them there. So if you want to build one of these filters, you can just download the files, make the PCBs, make the modules. It's all yours. And then to everyone who doesn't know, these streams, I only do them publicly live. And afterwards, I put them on my Patreon. So if you want to watch the replay, you will have to go to my Patreon and watch them there. And that is all. And I hope you guys have a good evening. Oh, there's more questions. Okay, let me answer these as well. Off-topic questions, but what is the tattoo on your right arm? You mean this one? This is, I think, a what's the English word? A piston, like from a motor. Just saw this somewhere. Thought it looked cool. I'm not a motorcycle guy, so. Have you got the date for your next stream in mind? I try to do a stream every Sunday, as long as I can come up with worthwhile topics, and as long as I'm not busy editing or filming a new video. So you can count on there being a stream on Sundays every time. And I will always try to announce them like two or 3 days in advance. More questions. Thanks for sharing. Yes, thanks for watching again. It's very, 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 very cool that you are all interested in this kind of stuff. Anything else? That is a spark plug. Yes, that's the English word. Exactly. Don't think the diodes would burn. Isn't it max 24 volts, 10 volt drop for the LEDs and 2K resistance series? Yeah, just someone warned me earlier that the reverse breakdown voltage of these diodes is not the same as with the small signal diodes, and that, you know, if you reverse bias them too much, that they could go poof. So that's why I went for the diode here. Might not be true, but that's something that you could probably try out yourself. Spark plug, yes, thank you. Will you support AFIX when you come to UK? It's very unlikely. This was an enjoyable stream. Thank you. That's glad to hear. Okay, so I will wrap it up here. Again, you can watch the replay on my Patreon. Thank you very much for watching, and I will probably see you next Sunday. Bye-bye.